In the boundless expanse of space, where we've long believed the universe stretches outward without limit, an unsettling thought begins to surface. What if we've misunderstood the true nature of the cosmos? What if, rather than forever expanding, the universe loops back on itself, reconnecting in ways we have yet to grasp fully? Like a snake devouring its own tail, the cosmos may curve and fold in on itself, suggesting a cyclical, self-contained structure instead of the endless sprawl we've imagined. This idea isn't just a fantastical musing. It's grounded in the frameworks of modern physics, where theories derived from Einstein's work open the door to the possibility of a universe that is finite but boundaryless. It's a universe that, much like the Earth, could be circumnavigated. In this model, if you journeyed in one direction long enough, you would eventually return to your point of origin. This concept challenges our most basic assumptions, presenting a reality where the universe isn't a never-ending expanse, but rather a looping system that might create a new, extraordinary way of understanding existence itself. One of the most compelling pieces of evidence comes from the cosmic microwave background, what is considered the oldest light in the universe. Within this background, scientists have begun to detect peculiar patterns that seem to mirror each other on opposite sides of the sky. These mysterious alignments could hint at regions of the universe that are, in essence, reflections of one another, much like parallel mirrors that display the same image from different angles. If these reflections hold true, it would suggest the possibility of a universe that, rather than stretching infinitely, folds back in on itself, creating a looped structure. If the universe were indeed a loop, the implications would be nothing short of profound. Time, as we know it, would no longer flow in a simple, linear fashion. The notions of past and future could dissolve into a cyclical dance, with events in the distant future potentially influencing those in the past. The arrows of causality would bend, perhaps becoming circular, reversing our understanding of cause and effect. The rigid flow of time, forward and fixed, could become a closed loop, endlessly repeating, where before and after no longer carry their traditional meanings. The concept of a looped universe is a fascinating and mind-bending proposition. It suggests that space and time might not only curve, but interlace in such a way that they fold back onto themselves, creating a finite yet unbounded structure. In such a model, a traveler journeying far enough in a single direction would eventually find themselves back where they started, completing a full circuit of the cosmos. This idea defies the conventional view of an infinite, flat universe, suggesting instead a structure that is not only finite in size, but uniquely connected upon itself in higher dimensions. As this hypothesis suggests, our universe might undergo cycles of expansion and contraction, with the Big Bang merely being one phase in an endless series of cosmic rebirths. Each cycle could represent a beginning, followed by an expansion, a contraction, and another rebirth, suggesting that the Big Bang is not an isolated event, but part of a larger cyclical pattern. This model proposes a universe that isn't just a one-time phenomenon, but a grand cosmic wheel turning through infinite epochs. Events might repeat themselves in a vast, eternal cycle, and time could become fluid, repeating not only the past, but reshaping our perception of the future. The consequences of a looped universe extend far beyond our everyday understanding of time and space. In such a universe, the concept of infinity would be redefined. There would be limits to how far we could travel or observe, even if those limits are staggeringly vast. This brings into question the very idea of the observable universe, raising the tantalizing possibility that beyond our current cosmic horizon, there may be more space, more structure, and potentially more knowledge that we have yet to grasp. A looped universe could help explain certain cosmological mysteries, such as the puzzling uniformity of the cosmic microwave background radiation. If regions of space were causally connected early in the universe's history, this might resolve the so-called horizon problem, explaining why the universe appears homogeneous despite being so vast. Yet, despite these tantalizing possibilities, there is no definitive observational evidence confirming that our universe is, in fact, looped. The idea remains speculative, yet it continues to captivate the imaginations of cosmologists and physicists, offering a new way to think about the structure and destiny of the universe. As this theory evolves, it forces us to challenge our place within the cosmos and reconsider everything we thought we knew about space, time, and existence. The notion of a cyclical universe is not a new one. Throughout history, countless cultures have proposed models of the cosmos that involve cycles of creation, destruction, and rebirth. In ancient Indian philosophy, particularly within Hindu and Buddhist thought, the universe was envisioned as an eternal wheel of time, known as the Kala Chakra, with periodic dissolutions and rebirths. This cyclical view mirrored the belief that the cosmos is subject to constant renewal, and time itself is not linear, but infinitely recurrent. Similarly, ancient Greek philosophers, such as Heraclitus and the Stoics, speculated about the idea of eternal recurrence. They believed that the universe repeats itself endlessly, with every event and circumstance occurring again and again in an infinite loop. These ancient ideas would later influence the German philosopher Friedrich Nietzsche, who famously incorporated the concept of eternal recurrence into his own works. The Mayans, too, conceived of time as cyclical, with their intricate calendar systems reflecting their belief in recurring ages, each of which would end in catastrophe, only to begin again in a new cycle. Ancient Egyptian mythology, with its depiction of the sun god Ra's daily journey, mirrored this concept of continuous renewal through cyclical patterns. In modern cosmology, the concept of a cyclic universe has been revisited in theories proposed by physicists like Paul Steinhardt and Neil Turok. Their epirodic model suggests that the universe undergoes endless cycles of expansion and contraction, with each cycle being triggered by events similar to the Big Bang. These contemporary models, while different from ancient philosophical ideas, still reflect a deep human fascination with cosmic cycles and the potential for perpetual renewal. At the same time, cosmologists are also exploring the idea of the multiverse, which offers a different, though equally intriguing, perspective on the nature of reality. While the looped universe suggests that our universe is self-contained and loops back upon itself, the multiverse theory proposes that there could be an infinite number of universes, each with its own distinct set of physical laws, constants, and initial conditions. The multiverse encompasses a variety of models, including the many worlds interpretation of quantum mechanics and the notion of bubble universes emerging from eternal inflation. Although the looped universe and the multiverse theory are distinct, both challenge our understanding of existence and stretch the boundaries of theoretical physics. A looped universe suggests a particular shape and structure to our cosmos, one that is finite yet unbounded, while the multiverse expands our view to encompass countless separate universes, each potentially offering a different version of reality. Both concepts provoke deep questions about the nature of space, time, and existence, pushing the limits of human knowledge. If the universe is a loop, it would have profound consequences for the laws of physics. The idea of causality, the principle that causes precede effects, would be called into question. In a looped universe, events could potentially cause themselves, leading to paradoxes that our current understanding of cause and effect cannot explain. This would require a complete rethinking of how time flows and how energy and matter are conserved. In such a closed-loop system, energy might be recycled endlessly, challenging our basic assumptions about entropy and the arrow of time. The ultimate fate of the universe, traditionally thought to involve heat death or collapse, might need to be reinterpreted in light of these new ideas. A looped universe doesn't just offer a new model for how the cosmos might be structured, it challenges our most fundamental notions of reality itself. Time, space, cause, and effect could all be reshaped by the possibility of an eternal, cyclical universe. In this view, our universe may not have a clear beginning or end, but instead exist as part of an infinite, looping pattern that continually renews itself, creating a reality that is far more mysterious and intricate than we ever imagined. Our understanding of the universe is poised for profound reconsideration, especially when we explore the intriguing concept of a looped cosmos. Such a model presents a finite, yet unbounded space, akin to the surface of a sphere, requiring a fundamental overhaul of our perception of space and cosmology. The implications ripple through the very foundations of how we interpret the cosmos, questioning not only the structure of the universe but also the laws that govern it. It forces us to reconsider the very nature of infinity and boundlessness, suggesting a universe that, while finite in extent, defies any form of boundary or edge. This looped universe concept stands in stark contrast to our current understanding of a limitless, static cosmos. The model's implications stretch deep into the heart of theoretical physics, particularly in the domains of general relativity and quantum mechanics, both of which have shaped much of modern scientific thought. A universe that loops back on itself necessitates a rethinking of how space and time function together, altering the way we consider the potential outcomes of cosmic expansion and contraction. The connection between entropy and a looped universe forms one of the most captivating challenges in modern cosmology. Entropy, often seen as a measure of disorder, dictates that any closed system will naturally evolve towards a state of maximum disorder and uniformity. This process, known as heat death, points towards the eventual decay of the universe into a cold, uniform state. However, the looped universe proposes a radical deviation. Rather than endlessly progressing towards greater disorder, the universe could reset itself after each cycle of expansion and contraction. This cyclical view of the cosmos suggests that each new cycle of the universe could, in theory, reverse the accumulation of entropy, offering a kind of cosmic reset button. Yet this scenario is not without its critics. One of the key challenges is the question of entropy's accumulation over successive cycles. If entropy increases with each iteration, it could result in longer and more extended periods of expansion, ultimately causing the universe to either expand forever or collapse into a final singularity. This progression poses significant questions about the limits of cyclical models and whether entropy's inevitable increase could halt the cycle altogether, preventing a true reset. The looped universe concept, therefore, forces us into a confrontation with the laws of thermodynamics, challenging the linear progression of entropy. It pushes the boundaries of cosmology, encouraging a closer examination of how we define disorder, balance, and the eventual fate of everything in existence. As we push deeper into these inquiries, we realize that the more we explore the concept of entropy in a looped universe, the more it underlines the complexity of reconciling thermodynamic laws with the more ambitious and speculative aspects of our cosmological models. At the heart of these investigations lies the theory of general relativity, which serves as the bedrock of our understanding of a potential loop universe. Developed by Albert Einstein, general relativity redefined our understanding of space and time, describing them not as separate entities, but as intertwined into a single four-dimensional continuum known as spacetime. According to this framework, the presence of massive objects bends and warps spacetime, creating the gravitational effects we observe. In the context of a looped universe, general relativity offers the mathematical tools to model how spacetime itself could curve on a cosmic scale, potentially allowing the universe to form a closed loop in higher dimensions. This model is radically different from the standard conception of an infinite, flat cosmos. General relativity doesn't just explain the way mass distorts spacetime, but also suggests the possibility of exotic geometries such as wormholes and closed, time-like curves. These concepts, though speculative, arise naturally from the equations of general relativity and propose paths through space and time that could loop back on themselves, forming the basis of a universe that returns to its own beginning. These predictions, while speculative, point toward phenomena that could potentially support a looped structure in the universe. The mathematical framework of general relativity also allows us to hypothesize how light and matter would behave in such a universe, offering models for how cosmic structures like galaxies might form and evolve in a closed cosmos. Furthermore, general relativity could provide a way to detect possible signs of this closed topology, particularly through observations of the cosmic microwave background radiation, which serves as a relic from the early universe and might contain subtle imprints of a closed cosmos. While general relativity provides a framework for understanding the possible existence of a looped universe, quantum mechanics adds another layer of complexity and intrigue. At the quantum level, particles do not behave according to classical physics, but instead exhibit strange properties such as superposition, where they can exist in multiple states at once. This phenomenon suggests that the nature of reality might be far more interconnected and fluid than previously understood, possibly permitting the formation of complex structures like loops at the cosmic scale. Quantum entanglement, a phenomenon where particles remain connected regardless of the distance between them, further reinforces this idea. This deep interconnectedness implies a fundamental unity in space and time, suggesting that distant regions of the universe might, in fact, be intrinsically linked in ways that support a looping structure. However, quantum mechanics also presents significant challenges to the looped universe concept. The uncertainty principle, a cornerstone of quantum theory, places inherent limits on our ability to measure certain pairs of properties, such as position and momentum, with precision. This uncertainty might complicate our ability to definitively confirm or deny the existence of a looped universe. Moreover, quantum decoherence, when quantum systems interact with their environment and lose their quantum properties, introduces another layer of difficulty. As we move from the quantum realm to larger macroscopic scales, maintaining the delicate quantum effects that might support a looped universe becomes increasingly complex. These issues suggest that while quantum mechanics offers tantalizing support for a looping universe, it might not be the final answer to the question. Despite these theoretical challenges, there are tantalizing clues in observational data that hint at the possibility of a looped universe. One such clue comes from the cosmic microwave background radiation, which provides a snapshot of the universe's infancy. Certain patterns detected in this radiation suggest the possibility that the universe might curve back on itself, forming a vast cosmic loop. Similarly, studies of the distribution of galaxies and galaxy clusters across the observable universe have suggested that their arrangement might follow repetitive patterns, potentially supporting the idea of a universe that loops back on itself. However, these findings are still hotly debated, and alternative explanations abound. Gravitational lensing, the bending of light by massive objects, also provides an intriguing avenue for exploration. In a looped universe, we might expect to see multiple images of the same distant objects, each appearing in different parts of the sky due to the curvature of spacetime. While some candidates for such multiple images have been identified, conclusive proof remains elusive. These observations, while compelling, do not offer definitive proof of a looped universe. The vast scales involved, coupled with the complexities of observing such phenomena, mean that confirming or refuting the looped universe hypothesis remains a significant challenge. Nevertheless, with advancements in observational technologies and methods, cosmologists remain hopeful that future data may offer a clearer picture of the universe's true structure and shape. An alternative model that has garnered increasing attention is the Big Bounce theory, which offers a fresh perspective on the universe's origins. Unlike the Big Bang theory, which posits a singular beginning for the universe, the Big Bounce suggests that the universe undergoes cycles of expansion and contraction. According to this model, the universe expands until it reaches a maximum size, then contracts under the influence of gravity, eventually collapsing in on itself. This collapse is followed by another expansion, starting the cycle anew. In this framework, the universe is not a one-time event, but part of an eternal series of cycles, each with its own birth, death, and rebirth. This cyclical view of the universe, much like the looped universe hypothesis, challenges the traditional notion of a singular cosmic beginning and suggests a more complex dynamic evolution of the cosmos, one that may offer new insights into the nature of time, space, and entropy itself. While still speculative, the Big Bounce presents a promising alternative to the linear, one-time universe we have come to accept, pushing the boundaries of cosmological thought and offering new avenues for exploration. However, this does not mark the end of the cosmic story. Instead, the immense energy and density at the point of collapse trigger a remarkable event, another expansion. This process initiates a new cycle, a perpetual renewal of the universe. The Big Bounce theory is deeply intertwined with the concept of a looped universe, where time and space are not viewed as a linear progression, but as part of a closed, cyclical loop. In this model, the end of one cosmic cycle effortlessly blends into the beginning of the next, creating a ceaseless cosmic dance of expansion and contraction. The Big Bounce provides a a compelling explanation for how this cycle unfolds, offering a mechanism through which the universe could transition smoothly from one phase to another. Proponents of this theory argue that it addresses some of the most puzzling problems in the Big Bang model, such as the singularity problem. According to the Big Bang theory, the universe begins as an infinitely dense point, a concept that clashes with our current understanding of physics. The Big Bounce, however, sidesteps this issue by proposing that the universe never reaches such an extreme state of infinite density. While the Big Bounce theory remains speculative and faces challenges, it offers an intriguing perspective on the universe's nature. It invites us to consider the possibility that our cosmos is part of a grand, eternal process, constantly renewing itself through an endless series of expansions and contractions. As cosmological inflation and the idea of a looped universe continue to spark curiosity, these concepts offer tantalizing possibilities for the structure and history of the universe. Inflation theory, for instance, suggests that in the earliest moments after the Big Bang, the universe underwent a period of exponential expansion, growing faster than the speed of light. This rapid expansion helped smooth out the irregularities that might otherwise have disrupted the formation of galaxies, stars, and planets, setting the stage for the universe we observe today. The idea of a looped universe presents an even more profound possibility. It proposes that the universe is finite but has no boundaries, much like the surface of a sphere. In this model, if you travel far enough in one direction, you would eventually return to your starting point. This idea, while seemingly at odds with the concept of a rapidly expanding universe, has prompted scientists to explore ways these ideas might reconcile. One possibility is that cosmic inflation could have occurred within a pre-existing looped universe, causing a small region to expand dramatically and become our observable universe. In such a scenario, our visible cosmos might just be a tiny part of a much larger, more complex structure, a looped universe that has existed for eons. Alternatively, the rapid inflation could have given rise to multiple universe bubbles, some of which could follow looped geometries. These hypotheses challenge our understanding of the cosmos, pushing us to rethink the very fabric of space-time. The interplay between these various cosmological theories highlights the complexity and ongoing exploration of the universe's true nature. As scientists continue to investigate these ideas, new observations and advanced mathematical models may help clarify how concepts like cosmic inflation and the looped universe could coexist, offering deeper insights into the universe's origins and future. The cyclic model, proposed by cosmologists Paul Steinhardt and Neil Turok, presents an alternative view on the universe's origin and evolution. According to this model, the universe does not have a single starting point, as suggested by the Big Bang theory. Instead, it undergoes endless cycles of expansion and contraction. In this vision, our universe is considered to exist on a brane, a three-dimensional surface within a higher dimensional space. These branes periodically collide with each other, and each collision sparks a new cycle of expansion. The energy released during these collisions is believed to be responsible for the creation of matter and the subsequent expansion of the universe. This cyclic model attempts to solve some of the problems the Big Bang theory cannot, such as the horizon and flatness problems. Rather than attributing the uniformity and flatness of the universe to a brief period of rapid inflation, this theory suggests that the effects of countless cycles have shaped the universe into its current state. While the cyclic model presents an innovative alternative, it is still a topic of heated debate within the scientific community. Researchers continue to examine its implications and seek observational evidence that could either support or refute this intriguing concept. The notion of a cyclical universe presents a radical shift in our thinking, suggesting that the cosmos is not a one-time creation, but a perpetually recurring process. Roger Penrose's conformal cyclic cosmology introduces another fascinating concept: a universe that exists in an endless series of cycles, each beginning with its own Big Bang and ending in a state of extreme expansion. According to Penrose, as the universe continues to expand and cool over vast timescales, all matter will eventually decay into radiation. In this state, the universe becomes scaleless, all particles reduced to massless photons. Penrose's theory hinges on the idea of conformal geometry, which focuses on the angles between objects rather than their size or distance. When the universe reaches this maximally expanded state, it is essentially indistinguishable from a highly compressed state, setting the stage for a new Big Bang. This creates a seamless transition from one universe to the next, forming an endless, continuous cycle. Each cycle, or aeon, as Penrose calls it, could have its own set of physical laws and fundamental constants, making each universe distinct from those that came before and after it. Penrose's theory stitches the end of one universe to the beginning of the next, creating a never-ending flow of cosmic birth and rebirth. Another alternative theory, the eternal eros, or erotic universe theory, proposes a different origin for the universe, one that doesn't stem from a sudden explosive event, but rather from the slow collision of two vast sheet-like structures called branes. These branes exist within a higher dimensional space and periodically collide, releasing immense energy that catalyzes the creation of a new universe. This collision ignites a cycle of expansion, cooling, and eventual contraction, culminating in another brane collision and the birth of yet another universe. This cyclical process challenges the conventional idea of a singular beginning to time and space, offering instead the notion of an eternal sequence of universes, each born from the remnants of its predecessor. Like the cyclic model, the erotic universe theory attempts to solve issues in the Big Bang model, such as the flatness and horizon problems, without relying on cosmic inflation. Although this theory is controversial and lacks definitive observational evidence, it continues to captivate the imagination of cosmologists as a potential alternative to the standard model of the universe's origin. In a looped universe, the geometry of spacetime takes on fascinating and counterintuitive properties. Rather than extending infinitely in all directions as we are accustomed to, a looped universe would curve back on itself, creating a closed but boundless structure. The implications of such geometry are profound, especially when considering how distance and direction might be perceived. For example, an object or light beam traveling in what seems to be a straight line would eventually return to its original point after traversing the entire universe. This phenomenon would occur across all three spatial dimensions, resulting in a complex, multidimensional structure akin to a torus. The curvature of spacetime in this looped universe would be positive, similar to the surface of a sphere but extended into higher dimensions. This geometry would lead to some fascinating effects. An observer might see multiple images of the same distant galaxy from different directions, as light from that galaxy would reach Earth by traveling along various paths around the looped universe. Time itself would also be impacted by this loop geometry. While the exact nature of temporal loops in such a universe is speculative, it is possible that time might exhibit cyclic properties, leading to scenarios where past, present, and future become interconnected in ways that challenge our linear understanding of time. A closed universe model further builds on this idea, where space curves back on itself like the surface of a sphere. In such a universe, space would be finite, but without boundaries. If you traveled in a straight line long enough, you would eventually return to your starting point, much like circumnavigating the Earth. This concept ties into the notion of a looped universe, suggesting that the universe could experience cycles of expansion and contraction. In this closed universe model, the total mass and energy would eventually be enough to halt the ongoing expansion caused by the Big Bang. Gravity would then take over, pulling everything back together in what some scientists describe as a big crunch. The loop concept proposes that this big crunch could be followed by another Big Bang, ushering in a new cycle of expansion and contraction. This endless cycle of cosmic rebirth mirrors the closed universe model, which envisions a finite yet unbounded cosmos that continually renews itself through periodic cycles. Current observations suggest that the universe is expanding at an accelerating rate, which stands in contrast to the idea of a closed universe. This notion of an ever-expanding cosmos challenges traditional models and theories. However, despite this, the concepts of a closed universe and cosmic loops continue to captivate scientists, sparking further research into the very nature and destiny of the universe itself. A looped universe, in particular, presents a tantalizing vision of the cosmos, one where the fabric of space itself might curve in ways that could defy our expectations. In such a universe, the curvature of space would not be uniform. It would fluctuate dramatically depending on the region, creating a diverse and complex cosmic landscape. Near massive objects like galaxies and black holes, space would bend sharply, distorting light and altering the trajectories of nearby celestial bodies. This would form regions of extremely warped space-time, potentially creating gravitational lenses that distort our view of distant galaxies and stars. These lenses would act like cosmic magnifying glasses, offering glimpses of distant parts of the universe in ways we might not otherwise observe. As we venture farther from these dense regions, the curvature of space would gradually flatten, becoming more pronounced in the vast, almost empty expanses between galaxies. In these cosmic voids, space would appear nearly flat, with only the subtlest fluctuations in curvature detectable through precise measurements. Yet, on the largest possible scales, the universe's curvature might loop back on itself, connecting distant regions in a way that seems counterintuitive. These large-scale connections would create a universe that, while vast, is closed in on itself, like a cosmic version of a Mobius strip. At the boundaries of this looped universe, we might encounter bizarre and perplexing visual phenomena. As we approach these cosmic edges, space could begin to curve even more dramatically, eventually wrapping around and connecting with the opposite side of the universe. This could result in multiple images of the same distant galaxy, as light would travel along different paths around the universe's looped structure. In such a model, the very concept of distance would be turned on its head, making it possible to see the same objects from different locations at the same time. These phenomena would challenge our conventional understanding of how light and gravity interact and fundamentally reshape our view of space. Understanding the variations in the curvature of a looped universe is essential for cosmologists who aim to study the large-scale structure of the cosmos. By mapping these curves and distortions, scientists can gain valuable insights into the distribution of matter and energy throughout the universe, shedding light on the forces that shape everything from galaxies to the very fabric of space-time. This understanding could also reveal much about the underlying nature of the cosmos itself, perhaps even offering clues about the mysterious forces that govern the universe, such as dark matter and dark energy. One possible model of a looped universe is that it could have a toroidal structure, like a giant donut. This would represent a dramatic shift in our understanding of cosmic geometry. The idea that the universe could have a finite volume but no boundaries would mean that it is possible to travel indefinitely in any direction, ultimately returning to one's starting point. This concept, reminiscent of circumnavigating Earth, presents a universe that is finite, yet infinite in potential, defying traditional ideas of edges and limits. Observers in such a universe might witness multiple versions of the same celestial objects, as light could potentially circle the entire universe, returning to its origin and giving the impression of repeating patterns across the sky. Galaxies, stars, and other cosmic bodies could appear simultaneously in different locations, depending on the observer's position and perspective. Such a toroidal structure would profoundly alter our understanding of the universe's size, shape, and structure. Its implications extend to fundamental concepts like gravity, the movement of light, and even the behavior of dark energy. Gravitational forces would behave in unusual ways, affecting everything from the orbits of planets to the paths of light itself. The shape of the universe would necessitate revisions to many of our established physical theories, particularly those dealing with cosmic inflation, the distribution of matter, and the nature of dark energy. This new framework could provide answers to some of the deepest mysteries of the cosmos, helping to unlock the secrets of the universe that have long eluded us. The task of detecting the curvature of a looped universe is an incredibly complex challenge. One of the most promising methods for studying this involves the cosmic microwave background, CMB radiation. The CMB, often referred to as the afterglow of the Big Bang, permeates the entire universe, and by studying its patterns, scientists can look for signs of repeating structures or unusual alignments that might point to the universe's true shape. In a looped universe, These patterns could show evidence of a cosmic geometry that loops back on itself. Another approach to detecting a looped universe involves studying distant galaxies and quasars. In a universe with a looped structure, it might be possible to observe multiple images of the same objects, as light could travel along different paths around the curvature of the cosmos. This phenomenon, known as topological lensing, could provide crucial evidence of a universe that loops back on itself. Advanced detectors, such as those designed to measure gravitational waves, might also contribute to this search. If gravitational waves were to travel around the universe's curvature, scientists might detect echoes or repetitions of these waves, further confirming the looped nature of the universe. In addition to observational methods, researchers are developing increasingly sophisticated mathematical models and computer simulations to predict the observable effects of a curved finite universe. These models are designed to simulate the distribution of matter and energy on cosmic scales, offering new insights into how a looped universe might behave. As our technological capabilities improve and our theoretical understanding deepens, we may uncover increasingly subtle signs that reveal the true shape of the universe. In such a universe, time itself would not behave in the linear one-way fashion that we experience. Instead, time would curve back on itself, creating what is known as a closed time-like curve. This implies that events in the universe could repeat in a cyclical manner, with the end of one cycle flowing seamlessly into the beginning of the next. Such a view of time would completely alter our understanding of cause and effect, as events in the future could potentially influence the past, giving rise to what physicists refer to as causal loops. From the perspective of an observer within this looped universe, time might appear to flow normally, with the conventional past, present, and future sequence. However, if one were to step outside this loop and view the universe as a whole, they would see that all moments coexist simultaneously, much like points on a circle. This aligns with the block universe theory, which suggests that the past, present, and future all exist as a kind of fixed block, with no true progression from one moment to the next. Instead, all moments are equally real. The implications of a looped universe on entropy and the arrow of time are profound. In our current understanding, entropy, essentially the degree of disorder in the universe, tends to increase over time, as described by the second law of thermodynamics. However, in a looped universe, this increase in entropy would have to reset periodically, raising intriguing questions about how the laws of thermodynamics would function in such a closed system. Would the universe reset itself completely, or would there be fluctuations in entropy that challenge our traditional understanding? The cyclical nature of time in such a universe presents a unique set of challenges and possibilities for physicists as they continue to explore the very foundations of reality itself. However, in a looped universe, time itself could fundamentally operate in ways vastly different from our conventional understanding. In such a cosmos, the fabric of space-time would curve back on itself, forming a structure where events cycle endlessly, never truly coming to an end, but instead perpetually repeating. This cyclical nature of time challenges everything we know about the flow of existence. Instead of progressing linearly from past to future, time in a looped universe might exist as a continuous loop, where the beginning and end of time are interconnected, creating an unbroken circle. In this imagined reality, time might not flow in the single unidirectional path we experience. It could potentially exhibit bidirectional properties where the past, present, and future exist simultaneously within a loop. This could result in paradoxical situations where causes influence their own effects, or events that are yet to happen could reach backward and alter their origins. This would create an entirely new paradigm where the arrow of time is no longer a clear and fixed direction. Even in a universe structured in such a loop, the subjective experience of time might remain unidirectional for observers. This perception of time moving in one direction could be influenced by what is known as the thermodynamic arrow of time. According to this principle, the increase in entropy, essentially the degree of disorder or randomness in a system, guides the flow of time as we understand it. As entropy increases, time appears to move forward, even though the underlying structure of the universe might permit a bidirectional flow of time. This tension between the cosmos's potential structure and our personal experience of time presents an intriguing conundrum. The very essence of time becomes uncertain, and as we delve deeper into these concepts, we are reminded of how much we still do not know about the true nature of time and the universe. While our current model of the universe sees time as a progression, flowing from the past to the future, guided by the second law of thermodynamics, the notion of a looped universe suggests a radically different approach. In this alternative model, the end of time might loop back to the beginning, creating a closed circuit of existence. Events could repeat over and over in an endless cycle, with time no longer having a clear start or finish. This cyclical structure would force us to reconsider the traditional concept of causality, the relationship between cause and effect, which is deeply tied to the flow of time. In a looped universe, cause and effect might become ambiguous or intertwined, with the past and future influencing one another in ways we cannot fully comprehend. Furthermore, the accumulation of entropy, something we expect to continually increase over time, could take on an entirely new role. In a universe with a looping structure, entropy might reset itself or redistribute at the point where the loop reconnects. This would challenge our understanding of the eventual heat death of the universe, the idea that all energy will eventually dissipate and the cosmos will reach a state of maximum disorder. In a looped model, this process of cosmic evolution and devolution could occur endlessly without ever truly reaching an end. The very concept of a looped universe forces us to confront some of the most profound questions about the nature of reality itself. What if time is not a one-way street, but a circular journey, constantly returning to its starting point while still moving forward? If the fabric of time is cyclical, what does that mean for our perception of memory, free will, and the way we experience the passage of time? This scenario invites us to think beyond the linear confines of our everyday lives and imagine a reality where time might be something far more complex. In theoretical physics, models have been proposed that explore the possibility of parallel universes or multiple timelines, each representing different outcomes of events. If we integrate the concept of a looped universe with the idea of multiple timelines, we find ourselves in a realm of endless possibilities. In such a cosmos, different timelines might exist simultaneously, each one a distinct thread in the larger tapestry of existence. These timelines could intersect, overlap, or even influence one another in ways we cannot predict. The looping nature of such a universe could result in an infinite cycle of these parallel timelines, creating a cosmic dance of endless variations and outcomes. Imagine that events from one timeline might spill over into another, creating cascading effects that ripple through the multiverse. These alternate realities, however, would remain theoretical. While these ideas are intellectually stimulating, they are currently not supported by direct observational evidence. Theoretical models and thought experiments remain the primary tools through which scientists explore these ideas, and while they expand the boundaries of our knowledge, they remain speculative at this stage. The implications of a looped universe are staggering, reshaping our understanding of fundamental concepts like cause and effect, free will, and even the very fabric of reality. Could events from one timeline affect another? Could we, in some way, become aware of these alternate versions of reality? These questions push the limits of our current understanding and inspire us to imagine a universe far more complex than we can fathom. As we continue to probe the mysteries of space and time, these radical ideas invite us to question everything we thought we knew. The looped universe, with its infinite cycles and potential for multiple timelines, challenges our conventional understanding of past, present, and future. Imagine time not as a line, but as a circle, with each moment looping back on itself. In such a universe, the boundaries between what has already occurred and what is yet to come become blurred, making us rethink our entire perception of existence. In this endless loop, events that seem far in the past could just as easily be part of the distant future. The end of the universe might not signify a conclusion, but a return to the beginning, starting the cycle anew. This continual looping could blur the lines of causality, making the connections between cause and effect less clear. In a universe governed by such cyclical patterns, The second law of thermodynamics, which states that entropy always increases, would need to be reconsidered. Perhaps in a closed-loop universe, entropy would remain balanced or even reset each time the loop closes, forcing us to rethink our assumptions about the long-term evolution of the cosmos. This vision of a looped universe is a mind-bending departure from our current understanding of time, space, and reality. It forces us to reconsider the most basic principles of physics, from thermodynamics to causality, and to think about time not as a river flowing in one direction, but as a cycle, an eternal return that is both familiar and alien at once. The exploration of this idea, though still firmly rooted in theoretical realms, could eventually lead us to new insights about the very structure of the universe itself. Moreover, the notion of a looped cosmos introduces profound and thought-provoking questions about the nature of free will and determinism. If the events of the universe repeat infinitely, one could argue that all actions and decisions are somehow predetermined, trapped in an endless cycle of repetition. However, the vast complexity inherent in such a monumental and ever-cycling cosmic structure may still allow for moments of deviation, unpredictability, and variance within each loop, preserving the essential notion of choice, possibility, and the agency of free will within a seemingly deterministic framework. This paradoxical tension between predestination and freedom challenges not only our understanding of the universe, but also the very nature of existence itself. In the context of a looped universe, the familiar ideas of a beginning and an end, of birth and death, lose their conventional meaning and structure. This cosmological model proposes that the universe is a closed loop, curling back upon itself through both space and time. In such a universe, the concepts of origin and finality are rendered nearly obsolete. Imagine journeying along a straight path through this looped cosmos. Eventually, you would find yourself back at your starting point, not because you have reached a defined endpoint and turned around, but because the very fabric of space-time itself has brought you full circle. The universe's vast curvature bends both space and time, rendering the notion of linear progression obsolete. This idea strikes at the core of our understanding of time, space, and causality. The traditional view of time, moving steadily forward with a clear beginning and end, begins to break down in a looped universe. In such a setting, every point in time could, in essence, be both a beginning and an end, depending on your perspective. The clear demarcations between past and future begin to blur as events may potentially influence themselves in an unbroken causality loop. This raises the intriguing possibility that the universe could be self-contained, perpetually renewing and sustaining itself without the need for an external origin or an external end. It is as if time itself becomes a continuous process of self-creation and self-maintenance. However, while the concept of a looped universe is undeniably intriguing, it remains speculative. Current observational evidence does not definitively support or refute this hypothesis, leaving cosmologists and physicists with much to explore and debate regarding the ultimate structure and evolution of the cosmos. Although compelling, the looped universe theory stands as an abstract idea, far from proven and subject to further inquiry and scrutiny. This concept offers a fascinating alternative to the traditional Big Bang theory, positing that our universe might not have a single definitive starting point in time. Instead, it could exist within an eternal, recurring cycle of expansion and contraction, continually transitioning from one phase to the next. In this model, what we interpret as the Big Bang may, in fact, be the transitional event that marks the shift from a previous cycle of contraction to the initiation of a new phase of cosmic expansion. This cyclical model suggests that our universe could be far older than current scientific models suggest, perhaps even infinitely old. The expansion would reach a peak size, only to be followed by a gravitational contraction, bringing everything back to a highly compressed state, triggering the formation of a new cycle. The idea that the universe cycles through periods of growth and contraction raises fundamental questions about the nature of time, causality, and the laws of physics. If the universe has no absolute beginning, it challenges the foundation of many cosmological theories that seek to explain the origins of the universe and the emergence of the fundamental forces of nature. What came before the Big Bang, and why did it happen the way it did? Perhaps the universe, in some form, has always existed, undergoing endless cycles of birth, death, and rebirth. However, there are significant obstacles to this model. It must address how the universe can avoid succumbing to the inexorable march of entropy, maintaining its ability to repeatedly expand and contract over infinite cycles. This challenge remains a central point of contention among scientists who continue to debate whether such a model is consistent with our current understanding of cosmology. In a universe that continuously cycles between expansion and contraction, the widely accepted idea of heat death, where the universe reaches a state of maximum entropy and thermal equilibrium, would no longer hold true. Instead of an eventual unchanging state of uniform energy distribution, the looping universe would experience periods of cosmic renewal. Each time the universe contracts under its own gravity, the matter and energy within it would condense into an ever more compressed state, potentially igniting the conditions for a new Big Bang. The intense pressures and temperatures during this contraction phase could essentially reset the universe, redistributing its energy and matter into a new, low-entropy configuration, which would fuel the next cycle of expansion. This cyclical view of the cosmos offers a radically different interpretation of the universe's ultimate fate, replacing the concept of irreversible decay with the promise of periodic rebirth. It envisions a universe that, despite its enormous scale and complexity, remains perpetually dynamic and self-renewing. Each cycle, lasting billions or even trillions of years, could represent a new opportunity for the formation of galaxies, stars, and planets, leading to a fresh chapter of cosmic evolution. The idea of a cosmic reset between each cycle provides a possible solution to the entropy problem, allowing the universe to avoid the inevitable heat death predicted by traditional thermodynamic models. However, even this notion faces significant hurdles. Would the universe truly be able to maintain this process indefinitely? Could it overcome the challenges posed by energy loss or degradation between cycles? These are questions that scientists continue to grapple with. In this looping universe model, the concept of multiple Big Bangs is a tantalizing possibility. Instead of a singular origin event, each new cycle could feature its own Big Bang, followed by an expansion phase and a subsequent contraction into a big crunch. This model suggests that our universe may not be unique, but part of an endless series of universes, each born from the collapse of its predecessor. However, this idea, while fascinating, clashes with our current understanding of the universe's acceleration, which points to an expanding cosmos rather than one contracting toward a singularity. The current rate of cosmic expansion raises significant doubts about the viability of a looping universe, leaving cosmologists to debate the future of this speculative theory. Despite the challenges and uncertainties, the concept of a looped universe continues to captivate the imaginations of scientists and philosophers alike. It challenges our perceptions of time, space, and causality, offering an alternative vision of cosmic evolution that eschews the finality of a single defining beginning. Whether or not the universe truly operates in such a cyclical pattern remains to be seen, but as we continue to explore the mysteries of the cosmos, the idea of a looped universe serves as a compelling reminder of the unknown and the infinite possibilities that lie ahead. However, scientists continue to delve deep into various theories concerning the ultimate fate of our cosmos, as well as the potential cyclical nature of the universe. The pursuit of unraveling the profound mysteries surrounding our universal origins and destiny has led to a thought-provoking concept: the notion of a looped universe. Within this framework, the idea of cosmic rebirth takes on an incredibly fascinating dimension. Picture this. As the universe expands, it stretches outward toward its maximum size, a vast and seemingly unending reach. But what happens when it reaches its peak? This immense expansion would eventually give way to a contraction, drawing everything back toward a singularity, where all matter and energy collapse into an incredibly dense state. This process, known to cosmologists as the Big Crunch, would mark the ultimate end of this cycle. But what if this collapse is not the end, but rather the beginning of another chapter? The concept suggests that after this Big Crunch, the universe might once again experience an explosive birth, a new Big Bang. From the remnants of the previous cosmos, a new universe would expand outward, carrying the echoes of the past, yet unique in its own right. This potential expansion and contraction could repeat indefinitely, creating a perpetual cycle of cosmic death and rebirth. Every cycle would present a fresh beginning, each universe with its own characteristics, shaped by the initial conditions and laws of physics that govern it. With each new iteration, the very fabric of reality could shift, creating diverse properties and structures that reflect the unique nature of each cycle. Some scientists speculate that, despite these new universes having slightly different fundamental laws or starting conditions, certain remnants of the past, whether it be information or physical characteristics, might transcend the boundaries of each cycle. These vestiges could somehow survive the transition from one universe to the next, hinting at a continuity that is both mysterious and profound. However, while the concept of a looped universe is intellectually captivating, it remains speculative, with the current observational evidence favoring an ever-expanding universe. This theory, though, continues to inspire ongoing scientific inquiry and philosophical musings, as it raises fundamental questions about the nature of existence, the universe, and our place within it. In the context of a looped universe, the behavior of matter would exhibit strange and captivating deviations from what we currently understand. Imagine this, a scenario where objects seem to appear multiple times from various angles. Picture yourself gazing through an incredibly powerful telescope, only to find the back of your own head staring back at you. This seemingly impossible phenomenon could be a consequence of the way light, having traveled across the vast expanses of the universe, might loop around and reappear, creating surreal reflections of reality. This concept challenges everything we know about the way light and matter interact on the largest scales. Such a looped structure would also influence the distribution of matter. Instead of the relatively uniform dispersion of matter we observe today, a looped universe might display striking patterns or symmetries that repeat at regular intervals. These patterns could offer vital clues to the size and shape of the universal loop itself, revealing insights into the very structure of space-time. Gravity, too, would behave in a radically different manner. Objects situated near one edge of the loop might experience gravitational influences from matter located on the opposite side. This could lead to unexpected cosmic phenomena, where galaxies form in ways that defy our current understanding of galactic evolution. Instead of following predictable paths, matter could curve and interact in entirely new ways, reshaping the structure of the cosmos itself. In such a universe, the concept of cosmic expansion would need to be reimagined. Rather than the straightforward expansion we observe today, which appears uniform in all directions, the expansion might be more complex. It could involve the stretching of the loop itself, an intricate process that creates new challenges in understanding the long-term fate of the universe. How would matter behave in such a scenario? How would it evolve over time, especially given the cyclical nature of the universe's rebirths? These are questions that remain largely unanswered, but are crucial to understanding how a looped universe might function. Energy, too, would follow a fascinating journey of transformation and conservation. In each cycle, as the universe expands and contracts, energy shifts between different forms while still adhering to the fundamental law of energy conservation. During the expansion phase, the universe cools and matter begins to form. Gravitational energy would convert into other forms, kinetic, thermal, and even electromagnetic energy. The birth of stars and galaxies would occur as lighter elements fuse into heavier ones, releasing immense energy in the process. This period of expansion would be marked by a dazzling array of energetic events, with the cosmos taking shape as new structures emerge from the primordial soup of matter and energy. But then, as the expansion slows and reverses, these galaxies and stars would begin to break apart, and energy would become increasingly concentrated. In the contraction phase, the universe would heat up dramatically, leading to a breakdown of matter into its most fundamental particles. Eventually, all forms of energy would merge into an incredibly dense, hot state, reminiscent of the conditions just before the Big Bang. It is during this phase that the universe effectively resets, preparing itself for another grand expansion cycle. Through this perpetual transformation, the total energy of the universe remains constant, yet its distribution and form change drastically. The universe would be in a continuous state of flux, evolving from one form to another, yet always bound by the unchanging law of energy conservation. In the context of a looped universe, dark matter and dark energy could play critical and distinct roles. Dark matter, the mysterious substance that interacts gravitationally with regular matter, might serve as the cosmic scaffolding that maintains the structure of the universe across its many cycles. As the universe expands and contracts, dark matter could act as a stabilizing force, ensuring that galaxies and large-scale cosmic structures retain their shape and form over time. This invisible presence would be the unseen architect, holding the universe together across infinite cycles. Dark energy, on the other hand, might serve as the driving force behind the expansion of each new cycle. Its repulsive nature could propel the universe outward, causing it to stretch and grow until it reaches a critical threshold. At that point, the cycle would reverse, and the universe would begin to contract. In this model, dark energy may not remain constant. Its strength could fluctuate, or even its properties could change throughout each cycle. It might switch from a repulsive force to an attractive one, adding an additional layer of complexity to the universe's cyclical nature. The interplay between dark matter and dark energy in a looped universe could create a delicate balance, one that would govern the entire life cycle of the cosmos. Dark matter would provide the gravitational pull necessary for contraction, while dark energy would fuel the outward push of expansion. This dynamic relationship could hold the key to understanding the duration, characteristics, and ultimate fate of each cosmic cycle, as well as the very structure of the looped universe itself. The behavior of dark matter and dark energy across multiple cosmic cycles may hold secrets that are yet to be unlocked. Over time, subtle imprints of these mysterious forces could appear in the cosmic microwave background, or perhaps influence the arrangement of galaxies across the universe. These remnants could offer us valuable clues not only about the cosmos as we see it today, but also about its past iterations, revealing the cyclical nature of the universe itself. Such evidence could dramatically reshape our understanding of the universe's structure, suggesting that the cosmos may not be a one-time event, but a recurring cycle of birth, death, and rebirth. In such a cosmic system, the principle of conservation of energy would be crucial. A fundamental law in physics, it dictates that energy cannot be created or destroyed, only transformed. In a cyclical universe, the total energy of the system would remain constant, despite the changes it undergoes through different forms and states. This means that as the universe cycles, we might observe dramatic transformations of energy on an enormous scale. For example, as galaxies, stars, and other massive cosmic structures collapse under their own gravity, the potential energy stored in their vast masses could convert into kinetic energy. This process would generate intense heat, radiation, and other forms of energy. Eventually, this energy would dissipate, and as the universe cools, it could reform into new structures, thus beginning the cycle anew. This model of a looped cosmic system challenges conventional views of entropy and the arrow of time. The second law of thermodynamics states that in a closed system, entropy, often understood as disorder, always increases. In a universe that loops, however, there must be a mechanism to reset or even reverse this process. How could a system continuously renew itself without defying the laws of physics? This question points to phenomena or forms of exotic physics that we have yet to fully comprehend or discover. A truly cyclical universe would raise the possibility of a cosmos that continually regenerates itself, potentially existing forever, defying the typical end-of-universe scenarios like the heat death or big freeze. Instead of cooling to a point of stasis, this kind of universe would perpetually evolve and transform, leading us to explore new realms of theoretical physics. As matter approaches the transition point of a cosmic loop, the conditions would become more extreme and unimaginable. The fundamental forces of nature, gravity, electromagnetism, the weak force, and the strong force, would behave in ways that are beyond our current understanding. Gravity, in particular, would grow in dominance. The effect of such intense gravitational fields could stretch and compress matter to an extent that we can barely envision, a phenomenon known as spaghettification. At the same time, time itself would begin to warp, its flow slowing down as observed from an external perspective. To the matter approaching the cosmic threshold, however, time could appear to speed up dramatically, as if the universe itself were folding in on itself. The fabric of space-time would undergo extreme curvature, distorting light and bending it in unpredictable ways, possibly creating gravitational lensing effects unlike anything we've observed. At this critical juncture, matter might undergo a dramatic phase transition. Atoms could be torn apart, breaking down into subatomic particles, which might even transform into forms of exotic matter that have never been observed before. In fact, some theories speculate that information about the matter's original state could be preserved on the surface of this transition point, much like how information is thought to be stored on the event horizon of a black hole. What happens to matter once it crosses this cosmic boundary remains one of the greatest mysteries in modern physics. Does it simply get recycled into a new universe, converting into pure energy, or does it undergo some other transformation beyond our current scientific framework? This transition represents the ultimate frontier of our understanding about the universe and its structure. In this sense, we are standing on the edge of what might be the greatest discovery in the history of science: the true nature of the cosmos itself. To contemplate the idea of a universe that forms a loop is to step into the realm of advanced cosmological theories. The topology of the cosmos, its shape and structure, plays a vital role in understanding how such a loop might work. The shape of the universe and how it may fold upon itself would depend on spatial dimensions beyond the three we experience in our daily lives. Theoretically, the universe could form a loop with as few as one spatial dimension, though such a model would be an overly simplistic representation of what might actually be at play. In more realistic scenarios, scientists have proposed that our universe could loop in 4 spatial dimensions. This is the essence of the closed or finite universe model, where, in theory, if you traveled in a straight line long enough in any direction, you would eventually return to your starting point, much like circumnavigating the Earth. However, the notion that our universe might be curved and finite rather than infinite contradicts current observations. Data from cosmological studies indicate that the universe is flat and possibly infinite, rather than curved and finite. Despite this, the question of whether space itself is finite or infinite remains unresolved, and scientists are continually refining their models to gain deeper insights into the true geometry of our cosmos. Additionally, advanced theories like string theory have proposed the existence of higher dimensional spaces, dimensions that are compact and smaller than those we can detect. These extra dimensions could also potentially form their own loops, too tiny for us to observe directly, but with profound implications for our understanding of reality. Cosmology, the study of the universe's origin, evolution, and structure, delves deep into questions like these, exploring how the universe came to be, its current form, and its ultimate fate. It examines the geometric properties of space, whether it is finite or infinite, flat or curved, and considers whether there are any unusual characteristics or configurations in its structure. One of the more intriguing concepts in this field is that of a looped universe, where space itself might be connected in such a way that it allows light and matter to travel in seemingly separate regions, eventually returning to their origin. Imagine the possibility of traveling through space for what seems like an endless journey, only to find yourself back where you started. In this model, the universe might be finite, but it would possess no true boundaries or edges. Such a structure might have emerged from the way space-time was shaped in the early moments following the Big Bang. The very fabric of the cosmos could fold back upon itself, creating a looped structure where space has no end, no beginning, only continuous circulation. This concept challenges our intuitive understanding of space, suggesting a reality where what we perceive as the universe is only a part of something much larger and far more intricate. If such a looped universe exists, it would revolutionize our understanding of everything from distant galaxies to the distribution of matter itself. It would imply that the cosmos is not a static, one-time event, but rather a dynamic, ever-renewing system. Such a universe would exist not only beyond our immediate understanding of time and space, but also outside the conventional limits of physical law. As we venture further into the study of this enigmatic cosmos, we must remain open to the possibility that our current models may be just the beginning of an even deeper and more profound understanding of the universe's true nature. However, the question of whether our universe might be looped remains tantalizingly unresolved, as current observations have yet to provide definitive proof for or against this intriguing hypothesis. The possibility of a looped universe extending into higher dimensions stirs the imagination, pushing the limits of our understanding of space, time, and the very nature of reality. At its core, the idea of a looped universe presents a challenge to our most basic intuitions about the cosmos, raising profound questions about the structure of everything around us. If such a universe were indeed a loop, the implications for how we observe distant galaxies and the distribution of matter throughout the universe would be nothing short of revolutionary. Despite the allure of this concept, however, conclusive evidence remains elusive, and the debate continues to unfold in the realm of cosmology. The possibility of higher spatial dimensions plays a crucial role in these speculations. In our everyday experience, we are limited to 4 dimensions, 3 spatial dimensions and 1 temporal dimension. But theoretical physics proposes that there might be additional dimensions beyond our perception. In a model of the universe that incorporates higher dimensions, our observable universe could simply be a small piece of a much larger multi-dimensional structure. These extra dimensions could be so tightly curled up that they are imperceptible to us at the scale we experience. Yet they may shape the overall geometry and topology of the cosmos in ways that we are only beginning to comprehend. These higher dimensions could hold the key to some of the most perplexing mysteries in physics. For instance, they might explain why gravity appears so weak in comparison to other fundamental forces, or offer new insights into the enigmatic phenomena of dark matter and dark energy. Moreover, these additional dimensions could provide novel ways for the universe to connect with itself, creating complex structures that extend far beyond the simple loops we envision. While these ideas remain speculative, they are consistent with mathematical models, and they continue to inspire researchers to think beyond the confines of our familiar 4-dimensional world. Despite their mathematical elegance, the existence of higher dimensions presents significant challenges when it comes to verification. Our current technological tools and observational methods are all constrained to the 4 dimensions we can directly perceive. Detecting or proving the existence of additional dimensions requires new ways of thinking and more advanced technologies than we currently possess. Nevertheless, the exploration of these concepts is far from stagnating. Rather, it is an area of intense focus that continues to drive the frontiers of theoretical physics, encouraging fresh perspectives on the fundamental nature of reality. One of the more compelling models for a looped universe is a 3-dimensional torus, often likened to a donut shape but existing in 4 spatial dimensions. In this model, our 3-dimensional space would be curved and connected in such a way that traveling in any direction would eventually bring you back to your starting point, much like walking in a straight line on the surface of Earth. This looping, however, would occur in all 3 spatial dimensions simultaneously, which creates a much more complex and intriguing structure than the 2-dimensional surface of the Earth. In such a 3-dimensional torus universe, the light from distant galaxies could arrive at us from multiple directions, potentially creating repeating patterns in the night sky. If the universe were small enough in relation to our observable portion, we might even see multiple images of our own galaxy from different angles. This looping structure could also give rise to strange phenomena, such as multiple versions of distant galaxies appearing in the sky, potentially offering new ways of viewing the cosmos. While the 3 torus is just one possibility, more complex shapes, referred to as hypersurfaces or manifolds, could exist in higher dimensions. These structures are difficult to visualize, but they are describable through mathematical models, and they could radically alter our understanding of space and time. String theory and its extension, M-theory, provide a theoretical framework that offers new ways of thinking about the looped universe. According to string theory, the fundamental constituents of matter are not point-like particles, but rather tiny, vibrating strings of energy. These strings exist in multiple dimensions beyond the 4 we can observe, with the potential for as many as 11 dimensions in total. Within this framework, the extra dimensions could be compactified, curled up in such a way that they are undetectable at our scale. One possible configuration for these extra dimensions is that they form closed loops, similar to a circle or a donut shape. In this setup, the universe could loop back on itself, creating a closed, self-contained structure that defies the traditional notion of infinite space. M-theory takes these ideas even further by introducing the concept of branes, higher dimensional objects that can interact with each other within a higher dimensional space. In this context, our universe could be a 3-dimensional brane floating in a space with more than 3 spatial dimensions. The loop nature of the universe could arise from the way these branes are configured or interact in the higher dimensional space. Furthermore, M-theory opens up the possibility of a multiverse, a collection of parallel universes, each with its own unique properties. Our looped universe might be just one of many, interconnected in ways we are only beginning to explore. Although these theories are still speculative and far from being experimentally verifiable, they offer a fascinating lens through which we can explore the nature of our universe. The idea that our cosmos could have a cyclical or looped structure potentially linking with other universes opens up mind-boggling possibilities that continue to drive the curiosity of cosmologists and theoretical physicists alike. Astronomers searching for evidence of a looped universe would likely begin with the cosmic microwave background radiation, CMB, the afterglow of the Big Bang. This faint radiation permeates the entire universe and offers clues to its earliest moments. Specifically, scientists would be looking for patterns in the CMB that could suggest that the universe has wrapped around on itself. One such signature would be the presence of matching circles in the radiation. If the universe were finite and looped, the same pattern of temperature fluctuations in the CMB might appear in different parts of the sky, indicative of light having traveled all the way around the universe. Another potential clue could be found in the large-scale structure of the universe. If space were indeed looped, we might observe repeating patterns of galaxy clusters and superclusters spread across vast cosmic distances. Detecting such repetitions would require incredibly precise measurements and an ability to track cosmic phenomena over incomprehensibly large scales. Additionally, gravitational waves, ripples in the fabric of space-time caused by massive objects accelerating through the universe, could provide further evidence. In a looped universe, these waves might travel around the entire structure, creating a distinctive interference pattern that could be detected by advanced gravitational wave observatories. Such patterns would offer critical insights into the shape and topology of the universe on the grandest scales. If the universe were indeed looped, finding repeated patterns or echoes in the cosmic microwave background would serve as a crucial piece of evidence. Cosmologists would seek areas in the sky where temperature fluctuations match precisely, suggesting that light has circled back to us after traveling through the entire universe. The challenge, however, would be immense. Any repetitions found would likely be subtle, distorted by the vast distances the radiation has traveled and the intervening matter and energy it has encountered. To detect these faint signatures, scientists would need to account for these distortions, using advanced statistical techniques and pattern recognition algorithms to sift through the data gathered by satellites and telescopes. Such a discovery would have profound implications for our understanding of the universe's shape, suggesting that the cosmos might be finite rather than infinite. Gravitational waves, too, could potentially reveal the looped nature of the universe. If the space-time fabric were indeed looped, gravitational waves might travel around the entire universe, returning to their point of origin and creating a distinct pattern of echoes in the data. These repeating signals would provide further evidence of a finite, closed universe, offering new insights into the structure of space-time and the vastness of the cosmos itself. Gravitational waves, the ripples in space-time generated by violent cosmic events, have the potential to reveal profound truths about the universe's early moments. Among these waves, those originating from the early universe, particularly during the era of cosmic inflation, hold tantalizing clues about the overall structure and scale of the cosmos. By studying these primordial gravitational waves, scientists might uncover faint signals that could indicate a looped, closed structure to the universe. However, uncovering such evidence presents monumental challenges. The signals from these waves would be incredibly faint, requiring instruments of unparalleled sensitivity and extremely sophisticated techniques for data analysis. Despite these formidable obstacles, advancements in gravitational wave detection could eventually allow researchers to explore new, groundbreaking insights into the fundamental nature and configuration of our universe. The idea of a closed universe model, which proposes that space curves back on itself in higher dimensions, has fascinated cosmologists for decades. This concept imagines the universe as a giant sphere where space loops back on itself, much like how the surface of a sphere connects seamlessly with itself. Detecting the exact point where the universe loops back on itself would be one of the most difficult tasks in cosmology. One possible method involves studying the cosmic microwave background, CMB, the afterglow of the Big Bang. This ancient radiation, which permeates the universe, could contain subtle imprints of the universe's shape. If the universe were closed, this radiation might have traveled around the universe multiple times, leaving behind repeating patterns or unusual correlations that could serve as signatures of its looped geometry. Another technique to detect this elusive looped structure involves measuring the geometry of space at the largest cosmic scales. By analyzing the angles of enormous cosmic triangles formed by distant galaxies, astronomers could potentially determine whether space is flat, open, or closed. In a closed universe, the angles of such triangles would add up to more than 180 degrees, whereas in an open or flat universe, the angles would behave differently. However, current observations suggest that the universe is remarkably close to being flat. This makes the detection of any curvature or looping structure exceedingly difficult with current technology. The sheer size of the observable universe, approximately 93 billion light-years in diameter, poses another significant hurdle for cosmologists. The vastness of the cosmos means that detecting any potential repetitions or patterns that could suggest a looped structure is an extraordinarily challenging task. Moreover, distinguishing between a truly looped universe and other cosmological phenomena that might produce similar observational effects complicates the search further. For example, certain patterns in the CMB might appear to suggest a looped universe, but they could also be the result of quantum fluctuations from the early universe or even observational artifacts. Time itself presents another barrier. If the universe were indeed looped, the time required for light to travel around the cosmic loop could exceed the current age of the universe. This would mean that even if we are living in a looped universe, the effects of this looping might be beyond our observational reach. We might be unable to detect any signs of looping within our cosmic horizon, which represents the farthest distance from which light has had time to reach us since the Big Bang. Moreover, our current understanding of physics breaks down at extreme scales and energies, particularly when it comes to reconciling quantum mechanics with general relativity. This gap in our theoretical framework makes it difficult to develop accurate models of a looped universe that can be tested through observations. The absence of a unified theory of quantum gravity makes it even more challenging to predict and confirm the existence of a looped structure in the cosmos. In a universe that loops back on itself, galaxy formation and distribution would exhibit unique and fascinating features. Unlike our observable universe, where galaxies are spread out in a vast cosmic web, a looped universe would create a more interconnected and repetitive structure. Galaxies in such a universe would form through the same processes of gravitational collapse and matter accumulation that we observe today. However, their distribution would be dramatically different. As light and matter travel through the loop, they would eventually return to their original starting point, producing a cosmic echo effect. This phenomenon could result in multiple images of the same galaxies appearing at various points throughout the universe, potentially creating the illusion of a much denser cosmos. The large-scale structure of the universe itself would also be altered in a looped universe. Rather than expanding infinitely in all directions, cosmic filaments and voids, those massive structures that form the backbone of the cosmic web, would take on repeating patterns as they loop back on themselves. This could lead to the formation of unusual galaxy clusters and might even create hotspots where multiple loops intersect, distorting our traditional understanding of cosmic evolution. The study of galaxy formation in such a looped universe would present astronomers with unprecedented challenges. Distinguishing between the original images of galaxies and those created by their looping paths would require highly advanced observational techniques. These challenges, however, also present an extraordinary opportunity to fundamentally reshape our understanding of cosmic evolution, revealing the deep nature of space-time itself. In this alternate, looped cosmos, the distribution of matter would be far more uniform and interconnected than in our current universe. Cosmic voids, vast, empty regions between galaxy clusters, and filaments, the thread-like structures connecting those clusters, are essential elements in the cosmic web of our universe. In a looped universe, these structures would be subject to unique gravitational influences and spatial constraints. The looping geometry would create repetitive patterns in the distribution of matter, potentially leading to a more regularly spaced and interconnected cosmic web. In this scenario, filaments might form closed loops instead of extending infinitely across the cosmos, altering the way we understand the very fabric of the universe itself. These distinct characteristics of a looped universe could offer a fresh perspective on cosmic structure. As we continue to push the limits of observational technology, particularly through advancements in space-based telescopes and gravitational wave detectors, we may one day be able to observe subtle cosmic structures that reveal the true nature of the universe's shape, size, and evolution. For now, though, the search for these signatures remains a formidable challenge, a challenge that could one day lead to revelations that transform our understanding of the cosmos forever. Furthermore, the finite nature of a looped universe could dramatically shape the size and structure of cosmic voids, marking a sharp contrast with the endless expansion envisioned in our current cosmological model. In such a universe, voids would no longer stretch out infinitely. Instead, their growth would be capped, determined by the dimensions of the universe's loop. This limitation would lead to a vastly different cosmic arrangement, with smaller voids and more pronounced filaments, resulting in a denser, more tightly packed cosmic architecture than what we observe today. The concept of a looped universe would radically transform our understanding of cosmic structure. Rather than an ever-expanding cosmos, we would be faced with a finite yet boundless space. Imagine embarking on a journey through space in a single direction, traveling for an inconceivably long time, only to find yourself back at the very spot where you began. This looped structure would not only shift our conception of space, but it would also change the way matter is distributed across the universe on the grandest scales. The cosmic web, consisting of galaxies, clusters, filaments, and voids, would take on new patterns, with regular repetitions occurring at vast distances. The universe itself would feel like a giant cosmic echo, an intricate loop of recurring structures. In this looped universe, we might witness these structures reappearing at regular intervals, creating a peculiar form of cosmic déjà vu. Galaxies, voids, and filaments of dark matter could mirror each other across vast distances, appearing as though they were echoes from the same cosmic melody. This could make cosmic observations perplexing for distant observers, as gravity would no longer operate solely in the conventional manner. The typical gravitational attraction between distant objects would now be influenced by the forces from their counterparts in the loop, subtly altering how matter is distributed across the universe. The behavior of light in this looped universe would also undergo a fascinating transformation. Light from distant galaxies would have multiple paths to reach us, potentially creating optical illusions or repeated images in the night sky. The implications for cosmological measurements would be profound, as astronomers would be forced to devise entirely new methods of observation and analysis to navigate the complexities introduced by the looping nature of space. At the heart of the looped universe model lies the notion of periodicity, an idea that if you travel far enough in one direction, you would eventually return to your starting point. This concept, often called a periodic or wraparound universe, suggests that large-scale structures such as galaxy clusters, voids, and cosmic filaments might repeat at vast intervals, possibly spanning billions of light years. Detecting these repetitions, however, would present monumental challenges. Our current technology can only observe objects near the edge of the observable universe, and these repeating patterns would likely lie beyond this limit. Furthermore, the expansion of space and the finite speed of light would complicate the detection of these distant repetitions, further pushing the boundaries of our observational capabilities. An intriguing possibility within this model is the potential for multiple images of the same galaxy or cosmic structure, but at different stages of its evolution. Imagine being able to study the same object, not just at a single point in time, but across different epochs of its existence. This would offer a unique glimpse into the long-term evolution of the cosmos, enabling scientists to observe how galaxies, clusters, and other cosmic features change over incredibly vast timescales. Such a prospect would provide insights into cosmic history that are unimaginable in a non-looped universe. However, detecting these repeating patterns is not without immense challenges. The most distant objects we observe are already on the edge of the observable universe, and any repetitions would likely occur far beyond this limit. The expansion of the universe, combined with the finite speed of light, means that these patterns would be incredibly difficult to detect, even if they exist. This looped universe model would also reshape our understanding of cosmic horizons. The traditional concept of a cosmic horizon, which limits our ability to observe distant regions due to the finite speed of light and the expanding fabric of space, would need to be rethought. In a looped universe, light from distant objects might take multiple paths through space, potentially leading to overlapping regions of observability. This would allow us to see not only further into the universe's past, but possibly observe the same regions of space from different angles or points in time. The observable universe would no longer be confined to a singular spherical boundary, but instead might consist of multiple overlapping horizons, each offering a different window into the cosmos. This shift would also force us to reconsider our interpretation of the cosmic microwave background radiation, which we currently regard as the faint afterglow of the Big Bang. In a looped universe, this radiation might have circled the cosmos multiple times, carrying with it information from various epochs of cosmic history. Each loop could contribute to the data we see today, making the cosmic microwave background a far more complex and multi-layered phenomenon than we currently understand. Gravity in such a universe would exhibit behaviors that defy our conventional understanding. In a closed, looped universe, objects could exert gravitational influence on themselves, with the gravitational effects traveling around the entire universe and returning to their point of origin. A massive object like a galaxy could experience gravitational pull from itself, as if the very fabric of space were reflecting its own presence. This would introduce new complexities in the way gravity shapes cosmic evolution. Moreover, the escape velocity, the speed an object must achieve to break free of a gravitational field, would change fundamentally in a looped universe. In our observable universe, objects must exceed a certain velocity to escape the pull of a gravitational well. But in a looped universe, no matter how fast an object travels, it would eventually loop back to where it started. This would create a kind of cosmic closed system, where nothing, not even light, could truly escape. Gravitational lensing, the bending of light due to the influence of massive objects, would also become far more intricate. Light from distant objects might take multiple paths through the universe, potentially passing around cosmic structures in various directions. This could create a Hall of Mirrors effect, where multiple images of the same galaxies or cosmic features appear in different parts of the sky. Mapping the universe in such a model would become an immense challenge, as the repeated images would create confusion about the true layout of cosmic structures. Perhaps most intriguingly, the fundamental forces that govern the universe, gravity, electromagnetism, and the strong and weak nuclear forces, might not remain constant across different regions in a looped universe. These forces are typically considered universal constants, but in a space that wraps around itself, the very fabric of space-time could distort and stretch. This distortion could alter the local strength of these forces. Areas of highly curved spacetime might experience stronger gravitational effects, while regions of less curvature might exhibit weaker gravity. The implications for the laws of physics and the very nature of reality itself would be profound. The predictable, uniform nature of the fundamental forces could give way to a more complex, localized variability in their behavior, challenging our deepest understanding of the universe. Furthermore, if the looped structure of the universe encompasses regions with varying energy densities or unusual distributions of exotic matter, these factors could dramatically alter the behavior of fundamental forces in localized regions. This concept introduces a vast array of possibilities for how the universe might behave on scales far beyond our current observational capabilities, presenting a serious challenge to our assumptions about the uniformity of physical laws across cosmic distances. The idea of a looped cosmos, where the very fabric of spacetime could fold back on itself in higher dimensions, could hold profound implications for the fundamental forces of nature, particularly electromagnetism. Electromagnetism, the force that governs the interactions of charged particles and the propagation of light, might exhibit peculiar properties on a cosmic scale within a looped universe. If space itself forms a closed loop, electromagnetic waves could theoretically travel around the entire cosmos, eventually returning to their point of origin. This raises the intriguing possibility that light from distant objects could take multiple paths through the loop, allowing us to observe several images of the same object from different directions. Such an occurrence would challenge our understanding of space, time, and light, creating a new way to think about the universe's geometry and our perception of distant phenomena. Additionally, the large-scale structure of a looped universe could affect the behavior of magnetic fields across cosmic distances. Unexpected patterns or alignments in the magnetic fields of galaxies and galaxy clusters might be explained by the geometry of space itself. These cosmic magnetic structures, shaped by the curvature of the looped space, could reveal fundamental insights into the nature of magnetism at a universal scale. The interaction between electromagnetism and gravity, an area of intense study in modern physics, could grow even more complex in this looped universe. The curvature of spacetime on such a grand scale would likely influence the propagation of electromagnetic forces, leading to entirely new phenomena that stretch our current understanding of both forces. In this looped framework, the strong and weak nuclear forces, though still expected to operate in much the same way as in our observable universe, might exhibit subtle variations due to the curvature of space itself. The strong nuclear force, which binds quarks together to form protons and neutrons, and the weak nuclear force, which is crucial for radioactive decay and nuclear fusion, are thought to be constant across the observable cosmos. However, the notion of a looped universe suggests that these forces might not behave uniformly across all regions. The looping structure of space could potentially lead to localized variations in the strength of these forces, subtly altering their manifestation over vast distances. This brings us to a fascinating question. How might the looped nature of the universe affect the uniformity of physical laws? The laws of physics, including those that govern the strong and weak nuclear forces, are generally assumed to be constant throughout the cosmos. But a looped universe, by its very nature, might introduce slight variations or gradients in the strength of these forces, depending on the specific geometry of space. This challenge to our assumptions about the consistency of physical laws invites a deeper exploration of the fundamental nature of the universe, one that could redefine how we view the very forces that shape matter. It is important, however, to note that these ideas remain theoretical. Our current observational tools and experiments have not provided definitive evidence for any significant variations in the fundamental forces across the observable universe. As such, the behavior of forces like the strong and weak nuclear forces in a looped universe is still a subject of speculation and active research in the fields of theoretical physics and cosmology. The exploration of a looped cosmos, though incredibly fascinating, remains an open question in science, and much work remains to be done before any definitive conclusions can be drawn. As we delve deeper into the possibility of a looped universe, we are compelled to consider the potential emergence of entirely new forces, forces that may not be accounted for in our current models of the cosmos. The idea of a universe that loops back on itself, possibly connecting distant regions of space and time, invites a host of potential new phenomena that challenge our established understanding of physics. In such a universe, the fabric of space-time itself might exhibit behavior that is completely alien to our current comprehension, leading to novel interactions between matter and energy. These newly imagined forces could manifest in ways that are currently undetectable, providing a pathway to insights into some of the greatest mysteries of modern science. For instance, these forces could offer new explanations for the elusive nature of dark matter and dark energy, phenomena that continue to perplex scientists and drive some of the most cutting-edge research in cosmology. However, as enticing as these possibilities are, it is crucial to remember that the notion of new forces emerging from the looped structure of the universe is still speculative. While the idea sparks curiosity, it remains far from confirmed. At present, scientists are actively searching for evidence of such phenomena using advanced observatories and experiments that probe the deepest reaches of the cosmos. This ongoing research could eventually shed light on whether the looped universe theory holds any merit, and whether these hypothetical forces are real or merely a product of our current lack of understanding. Quantum entanglement, a phenomenon that already challenges our understanding of the quantum world, becomes even more intriguing in a looped universe. In this context, the very fabric of space-time would curve back on itself, creating a closed loop rather than extending infinitely in all directions. In such a universe, when particles become entangled, they share a quantum state regardless of the distance between them. This entanglement defies classical concepts of information transfer, as changes to one particle instantaneously affect its entangled counterpart. In a looped universe, however, this phenomenon could take on even more perplexing characteristics. Imagine two entangled particles that are separated by billions of light years. In a universe with a closed-loop structure, these particles might actually be closer to each other along the looped path than they appear in a linear, expanding cosmos. This could lead to situations where entanglement effects seem to travel faster than light in one direction, but remain confined within the light speed limit when measured along the shorter looped path. Such a scenario would further stretch the boundaries of our understanding of quantum mechanics, possibly offering new ways to reconcile the paradoxes that currently arise when we attempt to unify quantum mechanics and general relativity. The potential implications of a looped universe on quantum entanglement could be vast, forcing us to reconsider not only the nature of space-time, but also the fundamental rules governing the behavior of particles. While these ideas remain speculative, they present exciting new avenues for research and could redefine the very fabric of reality itself. The looped structure of the universe, if it exists, may offer answers to some of the most profound questions in physics, pushing the boundaries of what we know about the cosmos, space, time, and the forces that govern everything in existence. In a universe that loops back on itself, particles might encounter their own past or future, entangled across vast cosmic distances. Imagine the intricacies of these quantum interactions, where time and space twist in on themselves. As particles travel through the cosmic loop, they may pass through each other's path, creating what could be described as closed time-like curves. These curves blur the boundaries of cause and effect on a quantum level, pushing the limits of our understanding of the universe. What if the rules of physics no longer held in such a scenario? These challenges not only test the fabric of quantum mechanics, but also expose the gap between what we know about gravity and the quantum world. This interplay suggests that new theories are urgently needed to unify these two fundamental forces. One of the most captivating phenomena in this realm is quantum tunneling. At the subatomic level, quantum tunneling allows particles to pass through barriers that classical physics would deem insurmountable. In the context of a cosmic loop, this concept becomes even more tantalizing. Although quantum tunneling is well understood for microscopic particles, its application to larger cosmic structures is far from clear. The likelihood of tunneling decreases significantly as the size or mass of the object increases. For larger systems, such as stars, galaxies, or entire cosmic loops, the probabilities drop to near zero. Yet, in the extreme environments of the early universe, or near singularities where the laws of physics break down, quantum effects may manifest on scales much larger than we've previously imagined. If tunneling could occur on these larger scales, it could potentially enable matter to jump across different points within the cosmic loop, leading to behaviors we cannot yet predict. But for now, this remains speculative, awaiting breakthroughs in both quantum mechanics and the elusive theory of quantum gravity. The uncertainty principle, a cornerstone of quantum mechanics, would also take on new significance in a looping universe. If the universe were structured as a closed, finite system, the very fabric of space and time would change. This alteration would transform the way particles behave, making it harder to pinpoint their position or momentum. In such a system, particles might interact with themselves across vast distances, creating a phenomenon known as self-interaction. These interactions add complexity to the uncertainty principle, as the past and future states of particles could begin influencing their current state. Furthermore, in such a closed universe, the maximum distance between any 2 points would be finite, limiting the range of possible momentum values. This, in turn, could lead to even more profound uncertainties, giving rise to new quantum phenomena unique to this kind of cosmic geometry. The uncertainty between position and momentum could manifest in ways we have yet to imagine, revealing new layers of quantum behavior that transcend our current models. The phenomenon of quantum entanglement would take on entirely new dimensions in a looping universe. Typically, entanglement occurs when two particles become linked, with their states tied together no matter the distance between them. But in a universe that loops back on itself, particles might become entangled with themselves, creating paradoxical situations where cause and effect become even more convoluted. This self-entanglement could introduce strange quantum effects, reshaping how we think about quantum mechanics and causality. In this framework, the quantum uncertainties between position and momentum could lead to a kind of entanglement that spans across not only space but time, further complicating our understanding of these phenomena. At the quantum level, fluctuations are always occurring. Particles pop in and out of existence, creating a dynamic, unpredictable backdrop to the universe. This quantum foam, as it is sometimes called, could have profound interactions with cosmic structures, such as strings and loops. These fluctuations might play a dual role in a looping universe. On one hand, they could help stabilize cosmic loops by providing small amounts of energy, counteracting the natural tendency for these loops to collapse. The constant fluctuations might act as a kind of cosmic scaffolding, supporting the loop over time. But on the other hand, these fluctuations could also become a destabilizing force. If they occur at specific points along a cosmic string loop, they might introduce enough instability to alter the loop's configuration, possibly causing it to break apart or reshape itself. This could result in the creation of new loops or the straightening of existing ones. The relationship between quantum fluctuations and cosmic strings remains an open question in theoretical physics, one that may redefine our understanding of both the smallest and largest scales of the universe. Quantum field theory, the framework that underpins particle physics, would also need significant adjustments to accommodate the concept of a looped universe. The very structure of space-time would differ fundamentally in such a universe, challenging our understanding of quantum fields and their interactions. One key modification might involve rethinking the nature of vacuum states. In a universe that loops, the lowest energy state of quantum fields could exhibit periodic behavior, reflecting the cyclic nature of space itself. This new understanding could lead to previously unimagined quantum phenomena, changing our interpretation of particle creation and annihilation processes. Entanglement, a cornerstone of quantum mechanics, would need reevaluation in this context. In a looping universe, particles could become entangled not only across vast distances, but also across multiple cycles of the universe. This could lead to a profound rethinking of quantum information theory, with implications for everything from communication to computation, and it might even alter our understanding of causality itself. Furthermore, the mathematical structure of quantum field theory would need to incorporate the topology of a looped universe, perhaps developing entirely new mathematical tools to describe field interactions on curved, closed manifolds. These developments could offer the key to a more unified theory that bridges quantum mechanics and gravity. Finally, in a looped universe, the potential for life to evolve differently in various regions is an exciting prospect. While the fundamental laws of physics would remain the same throughout, local conditions could vary widely. These variations could lead to different evolutionary paths, creating diverse forms of life across the universe. Regions with higher cosmic radiation might foster life forms with enhanced DNA repair mechanisms or protective outer layers. Moreover, the looped nature of the universe could give rise to regions with unusual elemental distributions or pockets of increased complexity. These localized variations might serve as catalysts for the emergence of entirely novel forms of life, potentially based on biochemistries we have yet to imagine. As the matter and energy cycle through the cosmic loop, they might give rise to new forms of existence, defying our conventional understanding of biology and chemistry. In this looping universe, everything from the behavior of particles to the evolution of life could unfold in ways we never expected. Every corner of this vast cosmos might hold secrets that challenge everything we know about the laws of nature. However, it is essential to recognize that the idea of a looped universe remains, for now, a theoretical construct, one that sparks intrigue and presents tantalizing possibilities, but is still far from being proven. While the concept of a looping cosmos offers endless potential for exploring the diversity of life, our current understanding of both cosmology and biology is still in flux. In the ongoing search for extraterrestrial life, we constantly challenge our existing assumptions, expanding our perspective on what life could truly be like beyond the confines of Earth. As we contemplate a universe with infinite loops, the implications for consciousness are profound. In such a universe, consciousness could undergo radical alterations. The very nature of time and space would not adhere to the linear progression we've come to know. Instead, these dimensions might become cyclical, continuously looping in ways that defy our basic comprehension. Imagine a reality where consciousness experiences repeated patterns, events, or even entire lifetimes, perhaps with no awareness of prior cycles. In this model, the distinction between past, present, and future might dissolve entirely, with consciousness accessing experiences and information simultaneously from what we would perceive as different points in time. This nonlinear perception could dramatically shift how beings process and interpret their surroundings, reshaping the entire framework of consciousness. Furthermore, in a looped cosmic structure, the very foundation of cause and effect might be entirely upended. Consciousness could struggle to distinguish between actions and consequences. In such a reality, events might influence their own causes, creating a circular form of causality where the usual sequence of time is broken down. This could lead to a fundamentally altered way of perceiving reality, where decisions and actions are no longer linear, but instead interwoven in an infinite feedback loop. The idea of consciousness in this universe might develop a heightened sense of interconnectedness with the cosmos, where the boundaries between the self and the environment become increasingly difficult to delineate. As a result, a more holistic and integrated form of awareness might emerge, one that transcends our current limitations and offers new ways of understanding both existence and consciousness itself. The concept of cosmic loops, often referred to as cyclic models of the universe, prompts even deeper questions about the preservation of information across unimaginable spans of time and space. In these models, the universe experiences repeated cycles of expansion and contraction, potentially stretching into eternity. The notion of preserving memory or information throughout these cycles is both fascinating and elusive. Conventional scientific understanding suggests that the extreme conditions at the end of each cycle, marked by overwhelming energy and density, would obliterate any traditional forms of data storage. However, some theoretical physicists have proposed speculative ideas on how information might persist through such extreme conditions. One concept involves quantum entanglement, where particles remain intertwined across vast distances, potentially allowing quantum information to survive the passage from one cosmic cycle to the next. Another hypothesis suggests that the fundamental constants of physics could carry remnants or imprints of previous universes, effectively creating a form of cosmic memory that endures across time. While these ideas are intellectually compelling, they remain highly speculative, lacking the empirical evidence needed to confirm them. The question of how memory is preserved in a looping cosmos continues to challenge our understanding of both the universe and the very nature of information itself, driving further investigation and philosophical debate on the fate of knowledge throughout the infinite cycles. In a looped universe, the concept of reincarnation could take on dimensions far beyond traditional understandings. Typically, reincarnation refers to the rebirth of a soul or consciousness into a new body after death. But in a universe that loops upon itself, the nature of existence and rebirth could be profoundly transformed. In a cyclic model, where the entire cosmos contracts and then restarts, the entire universe would be reborn, not just individual beings. Every event, every life, and every moment would recur in perpetuity. This cosmic reincarnation could add an entirely new layer of meaning to what we consider past lives and future incarnations. The implications for individual consciousness in such a universe would be staggering. We might speculate that our current existence is just one iteration in an endless cycle of universal rebirths. Under this model, we could have lived this same life countless times before, and will continue to live it again in future cycles. The boundaries separating past, present, and future lives would become indistinguishable, as all moments exist simultaneously across the multiple iterations of the universe. Despite its allure, however, it is important to note that these ideas remain speculative. While some cosmological models suggest the possibility of a cyclic universe, there is no scientific consensus on whether our universe operates in such a manner. Nonetheless, the concept remains a captivating thought experiment, one that forces us to question our most fundamental understanding of time, existence, and consciousness. Living within a looped cosmos would radically alter the way beings experience reality. Imagine traveling in what appears to be a straight line, only to find yourself back at your starting point. For the inhabitants of a looped universe, this would be the lived reality. Their entire understanding of space and direction would be reshaped by the knowledge that, with sufficient distance, one might eventually return to the same spot, a perpetual cycle within the fabric of their universe. Time itself could loop, leading to recurring events, perhaps even déjà vu on a cosmic scale. Celestial phenomena, previously thought to be unique or one-time occurrences, might unfold in predictable intervals, repeating in an endless cycle. This would not only challenge the traditional understanding of cause and effect, but could also have profound consequences for how inhabitants perceive and interpret their reality. The cyclical nature of the universe might make it difficult to discern where one cycle ends and the next begins. The idea of infinity would take on an entirely new meaning. While the universe may be finite in size, the possibility of traversing it endlessly would present a unique and unsettling philosophical conundrum. In such a cosmos, beings might develop completely new perspectives on life, death, and the concept of progress. The cyclical nature of their existence would shape their entire worldview. The idea of eternal recurrence would challenge notions of free will and determinism. If everything is destined to repeat, do individual choices matter, or are they merely predetermined by the cycles that have already come before? The concept of a looped universe also raises unsettling questions about the nature of identity and consciousness. If the universe repeats in its entirety, does that mean individuals live the same lives over and over, or do slight variations arise with each new cycle? This introduces profound questions about the continuity of the self and whether consciousness persists through these endless iterations, or is somehow recreated anew each time. Ultimately, the concept of an endlessly looping universe serves as a lens through which we can examine the most profound aspects of existence: time, identity, and consciousness. It forces us to confront questions that even now seem beyond our understanding. Does the universe truly loop? And if so, how would that reshape the very core of what it means to exist? The possibility remains an open question, one that beckons further exploration, investigation, and contemplation. Furthermore, the concept of a looping universe forces us to reconsider the very nature of progress and purpose. If everything eventually returns to its original point, can we still attach meaningful value to our actions, to the milestones we strive to achieve, or to the goals we pursue? The idea that events repeat in an endless cycle presents a paradox. It might provoke a sense of cosmic futility, as if everything we do is ultimately insignificant in the grand cyclical sweep of time. Or it could lead us to an entirely different realization, the idea that meaning may not lie in the end result, but rather in the moment itself. If every experience, no matter how fleeting, is both unique and eternal, then perhaps our true purpose is to appreciate the now, knowing that each fleeting second has its own value within the cosmic rhythm. The notion of cosmic cycles, where events inevitably repeat, further complicates our understanding of free will. If the universe undergoes expansions and contractions in a repeating pattern, where the same circumstances are potentially recreated with each iteration, what does this imply about our choices? Could the unfolding of the universe from one cycle to the next be a predestined path determining our every action? In this scenario, it would seem that free will is an illusion. Our choices are not ours to make, but are already written into the fabric of the universe's cyclical process. But this raises another question. Even if the events themselves repeat, does our perception of free will still hold? The illusion of choice remains intact for us, even if the circumstances surrounding those choices are part of a cosmic rhythm. The experience of making decisions feels genuine, and within each cycle, it seems as though we are empowered to shape our own destiny. However, this leads us to wonder, is this sensation of choice merely an illusion, a necessary aspect of our consciousness, a comforting delusion that allows us to experience life as though we are in control? Alternatively, one could argue that while the broader strokes of existence repeat, major events, key moments in history, even the very structure of the universe, there is room for individual choice within the confines of each cycle. Perhaps within the broader pattern, there exists a space where we can make decisions that alter the course of our own unique experience. In this view, free will might not be entirely an illusion. It could be understood as a limited form of freedom, a freedom that exists within each cosmic iteration. Here, our choices matter in the context of our current existence, even if they are part of a much larger, repeating process. Ultimately, the concept of recurring cosmic cycles offers a profound challenge to our understanding of free will. It forces us to confront the deep question of determinism and to reconsider the very essence of choice itself. As we contemplate the nature of reality, we are pushed to expand our understanding of consciousness, the self, and the universe. In a cosmos where cycles of time fold upon themselves, where events continuously repeat, we must ask, what does it mean to truly be free? In a universe that lacks a definitive beginning or an ultimate end, the very idea of existence is transformed. Traditional views of purpose often rest upon the idea of creation and finality, a beginning, a middle, and an end. But if the universe is eternal, an endless loop of expansion and contraction, then our place within it must be viewed in a radically different light. This eternal cosmos challenges our understanding of causality and time itself. Without a clear starting point or a final conclusion, the fabric of reality becomes an intricate, infinite web of interconnected events. In such a framework, existence might not be seen as a journey progressing from a fixed origin to a predetermined conclusion, but rather as an ongoing process of constant change and interaction. The meaning of existence in such a universe would not lie in any ultimate destination, but in the richness of the present moment. Each instant would be valuable in and of itself as a singular point in an infinite continuum. Our actions, rather than contributing to an overarching cosmic plan, might take on meaning through their immediate effects, the ripples they send through time and space. This perspective invites us to appreciate the inherent wonder of being alive. It suggests that the true beauty of existence lies not in the idea of a grand narrative, but in the perpetual unfolding of new possibilities, in the exploration of the unknown, and in the discovery of the self in the universe. The absence of a definitive beginning or end does not devalue existence. On the contrary, it elevates the significance of how we choose to live, how we choose to experience each moment, and how we interact with the infinite dance of the cosmos. In a looped cosmic system, the traditional notions of purpose and destiny undergo a fundamental transformation. In a universe where events are continuously recycled, linear progressions and final endings become less meaningful. The cyclical nature of existence challenges our understanding of cause and effect, for events in one cycle might influence or be influenced by events in another cycle. This intertwining of time and space complicates our perception of individual purpose. Instead of seeing purpose as the achievement of a singular goal, we might come to view it as playing a role in the ongoing cosmic dance. Each cycle offers new opportunities for growth, learning, and evolution. Wisdom accumulated in one cycle may carry forward, shaping the events of the next. In this view, the focus shifts from the destination to the journey. With each cycle presenting a new beginning, destiny is no longer a predetermined path, but a series of interwoven patterns that repeat, yet evolve with every iteration. This cyclical concept of destiny fosters a sense of cosmic interconnectedness. It suggests that our actions and choices have consequences beyond our individual lifetimes, extending across multiple cycles of the universe. The choices we make may echo across the endless expanse of time, shaping not only our personal experience, but the experience of all sentient beings throughout the eternal cosmos. Our role in this infinite dance is not defined by a singular purpose, but by the relationships we form, the actions we take, and the consequences of those actions that ripple across the very fabric of existence. The implications of a looped universe stretch far beyond the confines of individual lifetimes or even single cosmic cycles. If existence is not linear, but rather cyclical, then our understanding of purpose, identity, and being is fundamentally altered. We must come to see ourselves not as isolated beings, but as integral parts of an ongoing, ever-evolving story. This new perspective invites us to consider our place not just in the context of our own lives, but as part of a much grander, more complex, and ever-changing cosmic narrative. In such a universe, the idea of eternity takes on a profound new dimension. Instead of an endless, linear stretch of time, eternity becomes a series of cosmic reboots, each one giving birth to a new iteration of existence. Every cycle might recreate all matter and energy in a configuration similar to what came before. This endless looping nature of the cosmos presents intriguing questions about the nature of reality itself. If the universe is indeed cyclical, then it follows that events, even individual lives, may repeat infinitely. Time may not be a straight line stretching into the future, but rather a loop that folds back on itself. What does this mean for us as individuals? What does it mean for the very essence of existence? Could we truly experience life in a meaningful way, knowing that our actions might one day be repeated, that our very essence could be reborn in an endless cosmic cycle? The looping universe challenges the very core of how we understand reality, existence, and the nature of time. However, each cycle would likely exhibit subtle yet significant differences, as the principles of quantum fluctuations and chaos theory suggest that exact repetition is improbable. This concept of eternal recurrence, while at first glance a fascinating philosophical idea, carries profound implications for both our understanding of purpose and meaning within the vast expanse of the cosmos. In a universe governed by cycles, where the notion of time may fold back on itself over and over again, everything we know could be re-experienced, though never in quite the same way. The looped universe theory, as proposed by cosmologists, offers a refreshing perspective on the future of the universe. Instead of plunging into a cold, dark eternity as depicted in some other cosmic models, the universe would perpetually renew itself. This vision of a perpetual cycle of death and rebirth on a grand cosmic scale paints a picture of an existence that is, paradoxically, both ever-changing and repetitive. It hints at a kind of forever, not of stasis, but of continuous transformation, dynamic yet familiar, an eternal ebb and flow that cycles through infinite possibilities. As cosmologists delve deeper into this concept, they employ a vast array of sophisticated mathematical frameworks to investigate the intriguing possibility of a looped universe. One of the most prominent approaches to modeling such a universe draws on topology, the branch of mathematics that examines shapes and spaces. This framework allows scientists to envision complex, multi-dimensional universes that could loop back on themselves, creating closed geometries in which space is not infinite, but rather folds onto itself in a manner that seems almost impossible to visualize. In this model, traveling in one direction for an immeasurable amount of time might ultimately bring you back to your starting point, much like circumnavigating the Earth. Through the lens of topology, the universe is not merely a collection of isolated points, but a single, connected, and self-contained entity. Another key tool in the exploration of a looped universe is general relativity, Albert Einstein's groundbreaking theory that describes how gravity shapes the fabric of space-time. By applying advanced equations derived from general relativity, researchers can study how matter and energy behave in a universe that might be bent, twisted, or looped. These equations help scientists understand the movement of light, the flow of energy, and the interactions of matter in such a cosmic environment, where the very structure of reality itself could be curved in ways we can hardly imagine. In some of the most fascinating research, scientists are seeking ways to merge general relativity with quantum mechanics, just exploring the marriage of two seemingly incompatible domains of physics to better understand how the universe behaves at both its smallest and largest scales. Quantum mechanics, which governs the behavior of particles at the tiniest scales, plays a pivotal role in these models, especially when considering the early moments of the universe or the physics at extremely small scales. Quantum fluctuations, random deviations from the expected behavior of particles, could have profound effects on the universe's evolution. Some theories propose the integration of quantum mechanics and general relativity, leading to the development of frameworks such as loop quantum cosmology. This approach envisions a universe that undergoes endless cycles of contraction and expansion, an eternal bounce, where the cosmos continually collapses in on itself, only to explode outward once again, perpetually cycling through moments of birth and death. To investigate these mind-bending concepts, scientists rely heavily on computer simulations, which have become invaluable tools in testing the predictions made by these complex mathematical models. With the aid of powerful supercomputers, researchers are able to run simulations that model the behavior of a looped universe over vast timescales that span billions and even trillions of years. These simulations allow scientists to explore how the universe might evolve in a looping configuration, analyzing the behavior of matter and energy as they travel through a closed, repeating space. By simulating various cosmic parameters and initial conditions, researchers can observe how galaxies form, how dark matter behaves, and how other fundamental components of the universe evolve in a cosmos where time itself loops back upon itself. The potential consequences of a looped universe are far-reaching, and computer models have proven essential in predicting observable phenomena that might reveal whether our universe is, in fact, looped. For instance, by simulating the path of light through such a universe, researchers can investigate whether there are any unusual patterns or anomalies in the cosmic microwave background radiation, an ancient relic from the Big Bang that provides us with a snapshot of the early universe. These anomalies could, in theory, indicate that light has traveled around the loop of the universe, suggesting that the universe may not be infinite, but rather connected in ways we've yet to fully comprehend. Similarly, simulations can predict how gravitational waves, ripples in the fabric of space-time, might propagate in a closed universe, offering another potential method for detecting the looped structure. Moreover, these computer models enable cosmologists to probe how a looping universe might alter our understanding of fundamental concepts like the expansion of space and the distribution of matter. They offer the opportunity to predict the universe's ultimate fate by comparing simulated outcomes with real-world observations. By observing how different topological configurations influence the evolution of the cosmos, scientists can refine their theories and gain deeper insights into the true nature of space, time, and existence itself. Topology, as a mathematical tool, plays a crucial role in describing the shape and structure of a looped universe. It offers a framework for understanding how the cosmos might be connected, how it might curve or fold in on itself, and how the largest scales of space-time could form a continuous, unbroken loop. For example, consider the possibility of a finite but unbounded universe, a concept that challenges our most basic intuitions about space. Topologists propose that just as the surface of a donut is finite but unbounded, the universe could be similarly structured, an infinite loop within a finite space. This challenges conventional understandings of reality, forcing us to confront the idea of a universe that is boundless, yet somehow contained, leading to deeper insights into the very fabric of existence. One particularly intriguing aspect of topology and cosmology is its ability to potentially explain the patterns observed in the cosmic microwave background radiation. If the universe were indeed looped, certain repeating features might emerge in the radiation's distribution. These patterns could be the result of light traveling multiple times around the loop, bending and folding as it moves through the complex geometry of space-time. Such phenomena might suggest that the universe is not the infinite, ever-expanding space we once thought, but rather a finite, closed system that cycles through different configurations over time. As the universe undergoes these endless cycles, chaos theory reveals the unpredictable nature of this cosmic feedback loop. Each cycle, lasting trillions upon trillions of years, would not repeat in exactly the same way as the last. Instead, minute differences in the initial conditions of each cycle could lead to radically different outcomes, as chaos theory predicts. Even the smallest deviations could produce vastly different distributions of matter and energy, changes in fundamental forces, or variations in the constants of nature themselves. Over an infinite number of cycles, it's conceivable that the universe would explore every possible configuration allowed by the laws of physics. This concept is encapsulated in the idea of planar recurrence, the suggestion that, given enough time, the universe would eventually return to a state nearly identical to its beginning. Thus, a looped universe, far from being a monotonous repetition of events, would be a chaotic, dynamic entity. While the cyclical nature of time would bring certain things back again and again, it would never bring the same universe twice. Instead, each cycle would be marked by unpredictability, by subtle shifts in the cosmic order that might lead to entirely new configurations of the universe, yet always with a faint echo of the past, like the ripples left by a stone tossed into an infinite sea. However, the timescales involved in this theoretical framework are so vast that they would be almost impossible to fully grasp. The application of chaos theory to a cyclic universe raises some of the most profound and thought-provoking questions about the very nature of time, causality, and existence itself. Imagine a universe in which every cycle is both the effect of the previous cycle and the cause of the next, weaving a cosmic dance of interdependence. This creates a version of the chicken and egg paradox on a cosmic scale, where the boundaries between cause and effect blur, challenging our conventional understanding of temporal relationships. This interconnectedness across cycles forces us to reconsider our deeply ingrained linear perception of time. It hints at a deeper, more complex structure of reality than we currently understand, one that may defy the limitations of our existing paradigms. In order to describe this looped universe in its entirety, scientists might be required to create entirely new branches of mathematics, transcending the boundaries of current geometry and topology. We are faced with the prospect of constructing frameworks capable of accounting for the intricate and often paradoxical behaviors that could arise within a universe that folds back on itself, looping in ways we have yet to imagine. A potential key to unlocking this mystery lies in multidimensional manifolds, complex structures that may connect across vast cosmic distances. These mathematical constructs could offer a way to understand pathways through space that curve back on themselves, creating a reality where traveling in one direction might eventually bring you back to where you started. This would require us to develop mathematical models that can incorporate non-Euclidean geometry on a cosmic scale, pushing the very limits of our current understanding of curvature in space-time. Such models could allow for the bending and warping of space-time in ways that conventional mathematics cannot currently represent. In this new framework, even the simplest motions through the universe might not be as straightforward as we once assumed. Equally important in this endeavor would be the creation of mathematical frameworks that can describe causality and time within this looped universe. we would need to rethink the way time operates, transcending the linear progression from past to present to future. Instead, time could become a cyclical entity where events and actions are not just interconnected, but could potentially loop back and influence their own origins. This idea challenges the very essence of causality, an area of study that has been at the core of our understanding of physics and reality. To properly model this looped universe, we would have to consider paradoxes that could arise, such as events causing themselves, or realities where temporal relationships do not follow a simple cause and effect structure. In the end, describing a looped universe could require a synthesis of ideas from several of the most advanced fields of study, including quantum mechanics, general relativity, and the latest theories in mathematics. A new form of mathematics would need to emerge, one that seamlessly integrates these diverse domains into a unified theory capable of accounting for the unique properties of a universe that is, in a very real sense, self-contained and self-referential. This would involve not just refining existing equations, but creating entirely new methods to describe the behavior of energy, matter, and time in ways that are currently inconceivable. These new equations would need to account for the endless loops of the universe while revealing the cosmic mechanisms at work within them. Another fascinating and related idea is the theory of a fecund universe, which proposes that our universe might have the ability to spawn new universes, much in the same way a parent gives birth to offspring. This theory suggests that black holes, those enigmatic and powerful objects in space, could act as the portals through which new universes emerge. When a black hole forms, it might create a new universe on the other side of its event horizon, one entirely separate from our own. This concept ties into the idea of cosmic loops in a deeply intriguing way. Known as closed time-like curves, these theoretical paths in space-time could loop back on themselves, potentially linking parent and child universes in an unbroken chain of creation. In this context, cosmic loops might not only represent the cyclical nature of our own universe, but could also be pathways that connect multiple universes across vast stretches of reality. Each universe, according to this theory, would carry its own set of unique properties and physical laws. But these properties could evolve over generations. Just as biological offspring inherit traits from their parents, these universes could inherit physical characteristics from the universe that spawned them. Those universes with conditions conducive to forming black holes might be more likely to reproduce, in a sense, leading to a form of cosmic natural selection. While this idea remains highly speculative, it offers a fascinating framework for understanding the vastness and complexity of reality, beyond what we can currently observe. It challenges us to imagine that our universe may not be the only one, but rather a part of a much larger, ever-expanding multiverse. This multiverse could be connected through an intricate network of cosmic loops and black hole gateways, with each cycle of creation potentially leading to new, interconnected realities. One intriguing aspect of this theory is Lee Smolin's concept of cosmological natural selection, which extends the idea of black holes as birthplaces for new universes. Smolin suggests that black holes might give birth to new universes with slightly different physical constants and laws, each universe evolving through this process of cosmic reproduction. In the context of a looped universe model, where the universe goes through repeated cycles of expansion and contraction, Smolin's concept becomes even more fascinating. Each cycle of the universe could be viewed as an opportunity for cosmic evolution, with the physical properties of the universe being fine-tuned over time through a process similar to natural selection. As the universe contracts, it could potentially form a singularity, an event analogous to the formation of a black hole. From this singularity, a new cycle could emerge, but with altered characteristics, thereby refining the universe's constants. This process of universal refinement could explain why our universe appears so finely tuned for the existence of complex life and structures. Over numerous cycles, the universe might be optimized to create the ideal conditions for life, not unlike the gradual optimization of species through natural selection on Earth. This idea, though still in the realm of theoretical physics, opens up an entirely new way of looking at the universe. Instead of being a static one-off event, the universe could be a living, evolving entity, a cosmic organism that grows, changes, and adapts over time. And in this grand cosmic evolution, each cycle might not just be a repetition of the last, but a step forward in the fine-tuning of the very laws that govern everything from the smallest subatomic particles to the largest galaxies. However, it's important to note that both Smolin's concept and the looped universe model remain highly speculative. They are groundbreaking ideas that challenge our understanding of cosmic evolution and the very nature of reality. Yet, despite their allure, these theories currently lack definitive observational evidence to substantiate them. The bubble universe theory, for instance, posits that our universe is merely one of many universes existing within a far-reaching, overarching multiverse structure. According to this theory, each universe forms as a bubble in an ever-expanding cosmic foam. These bubbles are not static. They can grow, collide, and even merge with one another, creating a dynamic and constantly changing landscape of universes. Incorporating loops into this theory introduces an additional layer of complexity and intrigue. Some physicists speculate that within these bubble universes, space-time may form closed loops or cyclic patterns. This suggests that time, instead of following a linear progression with a clear beginning and end, could curve back on itself, creating a repeating cycle of events. This cyclical behavior of time could manifest in various ways within the bubble universe framework. One such possibility is that entire universes may undergo cycles of expansion and contraction, growing and shrinking over vast periods. Another intriguing proposition is that certain regions within a bubble universe might experience localized time loops, where events repeat within a specific area while the rest of the universe continues its evolution undisturbed. The combination of bubble universes and loops presents a captivating picture of reality. It envisions a multiverse teeming with diverse cosmic structures, each potentially following its own unique patterns of space and time. Such a view pushes the boundaries of our comprehension of existence, opening up fresh avenues for exploring the fundamental fabric of reality itself. The theories of eternal inflation and looped universes, while distinct in their approach, both attempt to explain the nature and structure of the cosmos, yet they do so from different perspectives. Eternal inflation proposes that our universe is part of a much larger multiverse in which new universes are continually being created. Space, in this model, expands at an exponential rate, driven by the energy of a quantum field. During this rapid expansion, quantum fluctuations can cause certain regions to stop inflating and form bubble universes, each with its own set of physical laws and properties. This process continues indefinitely, giving rise to what is known as eternal inflation. In contrast, the looped universe theory suggests a cyclical pattern where the universe expands from a singularity, reaches a maximum size, then contracts back into a singularity, only to expand once again in a new cycle. This creates a loop in time where the end of one universe seamlessly transitions into the beginning of the next. Though these two models might appear to contradict each other at first glance, some physicists have proposed ways to reconcile them. One possibility is that each cycle in a looped universe could give rise to regions of eternal inflation, which would create new bubble universes with each iteration. Alternatively, eternal inflation might occur within a larger cyclical framework, with each loop spawning its own inflationary multiverse. This suggests that the structure of our universe, or even the multiverse itself, could be far more interconnected and intricate than we currently comprehend. The concept of interconnected cosmic structures reaches far beyond our current observational capabilities, but theoretical models and emerging evidence suggest a multitude of intriguing possibilities. Astronomers have already identified vast cosmic structures such as galaxy filaments and supervoids, which together form a cosmic web stretching across billions of light years. These immense structures hint at the existence of even larger scale patterns in the universe, suggesting that our observable universe might be just a small part of a much grander cosmic landscape. Some theories propose that this landscape is, in fact, a multiverse, one that contains countless universes, potentially interconnected through higher dimensions or quantum entanglements. These connections could form intricate networks or loops that span distances far beyond our cosmic horizon. The notion of cosmic loops fits well within certain models of eternal inflation, where universes perpetually spawn new universes in an ever-expanding, fractal-like pattern. In such a scenario, our universe could be just one bubble in a vast cosmic foam, each bubble representing a distinct reality governed by its own physical laws and constants. The boundaries between these universes might form complex, intertwining structures at scales far beyond our current observational reach. While these concepts remain speculative, they are driving ongoing research in cosmology and theoretical physics. Advanced gravitational wave detectors, along with next-generation space telescopes, could provide new insights into these grand cosmic structures, unveiling evidence of even more complex and awe-inspiring cosmic architectures. As our understanding of the universe deepens, we may uncover phenomena that challenge our current perceptions of reality itself. In a looped universe, advanced civilizations might be able to harness the unique properties of such a cosmic framework for extraordinary feats of energy production and travel. One fascinating possibility is the creation of cosmic shortcuts. If space truly loops back on itself, civilizations might discover paths that connect distant regions of the universe, enabling rapid travel across vast cosmic distances. Additionally, the cyclical nature of a looped universe could offer opportunities for energy generation. By tapping into the enormous energies released during each cycle of universal collapse and rebirth, advanced civilizations might power themselves for eons. While speculative, this idea draws parallels to how we currently harness renewable energy on Earth, offering a vision of the future in which civilizations use the natural rhythms of the cosmos to sustain themselves and explore the universe. In a universe potentially governed by looping principles, the idea of advanced civilizations mastering the mechanisms that underlie space-time itself becomes a captivating prospect. These civilizations might, through an extraordinary understanding of cosmic mechanics, harness the very forces that make the universe loop. This could lead to the development of technologies capable of manipulating the fabric of reality, creating localized regions where the flow of time folds upon itself, closed time-like curves, which might serve as temporal highways. These highways would allow for travel between different epochs of the same cosmic cycle. However, the concept of a looped universe remains firmly within the realm of speculation, as the evidence to support or disprove it has yet to be definitively found. While we continue our pursuit of cosmic knowledge, the limits of our current understanding of cosmology leave many questions unanswered. At present, the notion of a looped universe is a theoretical concept that stretches our imagination, captivating both scientists and science fiction enthusiasts. Despite the allure of such an idea, modern scientific models do not substantiate the existence of such a cosmic structure. Our current understanding, based on general relativity and observational data, suggests that the universe is expanding, and it appears to be doing so at an accelerating rate. This rapid expansion makes the notion of a looping structure less plausible, as the vast distances between celestial bodies and the immutable speed of light stand as formidable barriers to any form of faster-than-light communication. In fact, faster-than-light communication, a long-standing pursuit in theoretical physics, would challenge the very foundation of causality, the principle that cause must precede effect. The violation of this principle could result in paradoxes that defy our most fundamental understandings of reality. While certain theoretical concepts, such as wormholes or quantum entanglement, have been proposed as potential solutions for faster-than-light information transfer, they remain speculative and unproven. Wormholes, if they exist, would require exotic forms of matter and energy to stabilize, while quantum entanglement, although a proven phenomenon, cannot transmit classical information faster than light, according to current understanding. Thus, while the quest for faster-than-light communication is a compelling subject of study, it remains far beyond our grasp. Time travel, on the other hand, is one of the most tantalizing concepts associated with a looped universe. If the structure of the universe were to curve back upon itself, the lines between past, present, and future could become far more fluid. One of the most intriguing possibilities in such a universe is the concept of closed time-like curves. These curves, if they exist, could theoretically allow an object or even a person to travel back to their original point in both space and time, creating the possibility of temporal travel. Yet, this concept brings with it a slew of paradoxes, none more famous than the grandfather paradox. If a time traveler were to journey into the past and alter events that lead to their own birth, could they undo their existence? This presents a complex dilemma that even theoretical physicists struggle to resolve. To counter these paradoxes, some theorists propose that the laws of physics may inherently prevent such contradictions. The Novikov self-consistency principle, for example, suggests that any time travel within a looped universe would be restricted to actions that preserve the consistency of historical events. In this model, time travelers would be unable to alter the past in ways that create paradoxes, ensuring that the timeline remains unbroken. The continuous expansion of human knowledge and technology has enabled us to explore the cosmos in unprecedented ways. However, our current view of the universe is constrained by the cosmic horizon, the limit of the observable universe determined by how far light has traveled since the beginning of the cosmos. While this horizon defines what we can see, it does not necessarily represent the full extent of the universe. Thanks to advancements in telescope technology, we can observe distant galaxies, some of which existed when the universe was just a fraction of its current age. Yet, as space continues to expand, light from even more distant regions is stretched and redshifted, making it increasingly difficult to detect these faraway objects. This stretching of light represents a significant challenge to our observational capabilities, but it has also driven scientists to explore alternative methods of exploration. Gravitational wave detectors, which sense ripples in space-time caused by cataclysmic cosmic events, offer one promising avenue to peer deeper into the cosmos. These ripples can carry information about the universe's most violent occurrences, allowing us to study phenomena that are beyond the reach of traditional optical instruments. Similarly, neutrino detectors have the potential to reveal information from regions far beyond our current observational horizon. Neutrinos, elusive particles that can pass through matter almost undisturbed, offer a unique opportunity to learn about distant cosmic phenomena. In the future, quantum technologies and artificial intelligence may provide additional breakthroughs, allowing us to process complex signals and refine our understanding of the universe. These innovations could open the door to new frontiers in space exploration, unveiling hidden aspects of the cosmos that are currently beyond our reach. The pursuit of advanced propulsion systems, capable of transcending the limits imposed by relativity, continues to capture the imagination of scientists and theorists. The concept of the Alcubierre drive, a theoretical spacecraft propulsion system, proposes the creation of a bubble of space-time around a spacecraft. By contracting space in front of the ship and expanding it behind, the Alcubierre drive could allow the ship to travel vast distances without violating the fundamental laws of physics. Similarly, the Tipler cylinder, a massive rotating cylinder, could, in theory, create a closed time-like curve that might enable time travel. While these ideas remain speculative, they represent the forefront of our theoretical understanding of space-time manipulation. Wormholes, often depicted in science fiction as shortcuts through the fabric of space-time, could also function as potential devices for interstellar travel or even time travel. These hypothetical tunnels could connect distant regions of space or even different moments in time, though the challenges of stabilizing and traversing them remain immense. Quantum loop engines, devices that could harness the strange properties of quantum mechanics, might one day enable new forms of propulsion or energy generation. One potential idea is to exploit quantum entanglement to transmit matter or information instantaneously across vast distances, though such technology is still purely theoretical. Finally, the age-old dream of perpetual motion machines, which would provide infinite energy with no loss, continues to spark curiosity, even though such devices are impossible under our current understanding of thermodynamics. Nonetheless, the drive to minimize energy loss and improve efficiency in technological systems is a central focus of modern science, pushing the boundaries of what is achievable within the known laws of physics. The concept of a looped universe raises profound questions, not just about time travel, but about the nature of reality itself. While the idea of closed time-like curves suggests that the universe could fold back on itself, it's crucial to understand that even if the universe were structured this way, it wouldn't necessarily lead to a perfect repetition of events. The complexity of the universe, with its countless variables and interactions, coupled with the uncertainties introduced by quantum mechanics, would mean that the outcomes of events could differ even when the initial conditions were similar. This introduces an element of unpredictability, ensuring that a looped universe would not necessarily be a perfect replica of the past. The interplay of chance and determinism remains one of the most profound mysteries in both cosmology and the philosophy of time. The sheer scale of the universe is an astonishing concept, one so vast that even if it were to loop, the time involved would stretch far beyond the limits of human comprehension. Imagine the unimaginable. The current age of the universe is thought to be about 13.8 billion years, but a hypothetical looped universe could stretch across a time span that would dwarf this, extending far beyond the reaches of any human lifespan. In such a scenario, any potential repetition of the universe would take place on scales of time so staggering that they become almost impossible to grasp. However, it's crucial to note that the idea of a looped universe is still highly speculative. The universe's structure, as currently understood, does not support the existence of such a loop. Observational evidence leans toward the concept of a flat or open universe rather than a closed, looping one. Despite this, cosmology is a field of constant discovery, and new theories are emerging all the time, pushing the boundaries of what we know about the cosmos. The notion of a repeating universe is still on the fringes of modern scientific thought, and as our understanding evolves, so too does our exploration of these tantalizing possibilities. If such a cosmic cycle were to exist, subtle variations could emerge in each iteration of the universe. These differences could arise from the tiniest quantum fluctuations, the barely detectable vibrations that happen on the smallest scales of existence. These minute deviations might influence the distribution of matter and energy during the universe's expansion, causing slight shifts in the arrangement of galaxies or the formation of cosmic structures. Think of it like shuffling a deck of cards, where the cards are the building blocks of our universe. Each new shuffle could result in a slightly different configuration, a unique arrangement that may only appear marginally different, but has the potential to spiral into something entirely distinct over vast periods of time. The very constants that govern our universe, things like the strength of gravity, the speed of light, and the properties of subatomic particles, could shift infinitesimally from one cycle to the next. These slight changes would have profound effects on the physical laws that govern each iteration of the cosmos, resulting in a universe that might operate under subtly different rules each time. Even the mysterious forces of dark matter and dark energy, which continue to baffle scientists, could evolve in new ways with each cycle. The rate of cosmic expansion, the formation of galaxies, and the distribution of matter might all vary across these hypothetical cycles, leading to universes that differ not just in shape or structure, but in the very way they exist and evolve. Over countless iterations, these small variations could accumulate, leading to entirely different outcomes for the cosmos. What may start as a slight change in one iteration could snowball into a dramatically different universe in the next. While the universe may appear nearly identical in each cycle, the cumulative effect of these subtle changes might give rise to a cosmos that is never quite the same, no matter how many times it loops. This idea raises fascinating questions about the nature of cosmic diversity, suggesting that even in a cyclic universe, no two iterations of the cosmos would ever be identical. The concept of a cyclic or looped universe often ties into the idea of eternal return, an intriguing and philosophical notion that proposes that everything that has ever occurred in the universe will eventually repeat exactly as it was before, in an infinite loop. The cyclical nature of existence raises profound questions about the nature of consciousness and memory. If the universe were to go through a series of expansions and contractions, repeating endlessly, what happens to the memories and consciousness of those who live through it? One significant challenge in this scenario is the fate of consciousness. Current understandings of consciousness are deeply intertwined with the physical structures of our brains and the laws of physics that govern our universe. If the universe were to contract and experience a big crunch, the extreme conditions would likely tear apart all known forms of matter and energy, including anything that might store consciousness or memory. The intense gravitational forces and extreme energy densities involved would obliterate any trace of individuality, erasing any potential for memory to persist through cycles. Moreover, if a new cycle of the universe were to begin, it would most likely reset all physical parameters and initial conditions. This reset would erase any lingering traces of information from previous cycles, making it extraordinarily unlikely for any form of consciousness to persist from one cycle to the next. In this model, even the fundamental constants of nature could be altered, further complicating the notion of continuity across cycles. Some speculative theories suggest that higher dimensions or parallel universes might offer a way for information to be preserved, but these ideas remain purely theoretical and lack empirical support. Thus, the question of whether consciousness can transcend the boundaries of a cyclic universe remains firmly in the realm of philosophical speculation. The idea of encountering alternate versions of ourselves from different cycles of the universe raises intriguing questions about identity and reality. Such a scenario implies the existence of a multiverse, where different versions of ourselves might exist in parallel universes, each having made different choices or lived through different experiences. The implications of this are profound, as it would provide tangible evidence for the many worlds interpretation of quantum mechanics. According to this theory, every possible outcome of a quantum event occurs in its own parallel universe, creating an ever-expanding multiverse where all possible histories and futures are realized. Meeting alternate versions of ourselves would be groundbreaking, confirming that all these parallel realities are not just abstract possibilities, but actual worlds. Such encounters would also challenge our notions of free will and determinism. If we were to meet versions of ourselves who had made different decisions, it would raise complex questions about the nature of choice and the role of chance in shaping our lives. Could our decisions be truly free, or are they the inevitable result of a deterministic chain of events? This realization could lead to deep philosophical debates about the nature of the self and the role of fate in our lives. At the same time, these encounters could offer tremendous opportunities for growth and learning. We could gain insights into different life paths, scientific discoveries, or technological advancements that our own version of the universe might have missed. The potential for knowledge exchange between alternate versions of ourselves is both exhilarating and daunting, but it also opens the door to unparalleled personal and scientific growth. However, such interactions might not always be positive. The existence of multiple versions of ourselves could lead to identity crises, psychological distress, or even conflicts, as each version might believe its reality to be the correct one. In a looped universe scenario, the idea of eternal return presents a fascinating dimension to the concept of cosmic cycles. In this model, everything that has ever happened could repeat over and over, endlessly. Picture this. The universe expands to its maximum size, then contracts back in on itself in a big crunch, only to be reborn once again in another Big Bang. In this cycle, the same stars, planets, and even living beings might form again and again, repeating their entire existence in each cycle. This cosmic recycling would mean that every moment, every encounter, and every decision might be destined to repeat endlessly, an eternal loop stretching throughout infinity. While this idea is captivating, it remains speculative. The concept of eternal return, while intriguing, doesn't align with current scientific observations. Most evidence points to a universe that is continuously expanding, with no sign of a cyclical collapse. Thus, the notion of an infinite, repeating universe remains a fascinating thought experiment, rather than a likely reality. Nonetheless, it provides a powerful philosophical puzzle and an exciting concept to ponder, as it challenges our understanding of time, existence, and the nature of reality itself. As we push further into the observable universe, we encounter the concept of an edge, where the cosmos might loop back upon itself. This idea suggests that our universe could have a finite size and shape, possibly creating a boundary that connects back to itself in ways that defy conventional understanding. If such an edge exists, we could witness phenomena that break the rules of physics as we know them. Light and matter could behave in strange and unexpected ways, potentially mirroring or repeating themselves as they cross this boundary. Imagine galaxies or large-scale structures duplicating or distorting, creating a cosmic hall of mirrors. At this hypothetical edge, the very fabric of space-time could warp and bend in unprecedented ways. The distinction between one place and another could become blurry, with objects potentially existing in multiple locations at once. This could lead to mind-bending scenarios where traveling in one direction might bring you back to your starting point, but from the opposite side. While these ideas are fascinating, they remain speculative. Current observations have not provided conclusive evidence for such a cosmic structure. Many scientists believe the universe may be infinite or at least far larger than our observable portion, making the existence of such a boundary seem unlikely. Even so, the exploration of these concepts is vital, pushing us to consider new and innovative ways of understanding the nature of our universe. By contemplating the possibility of cosmic loops, we stretch the boundaries of our knowledge, inspiring us to ask bigger questions and reach further into the unknown. It's through this pursuit of knowledge that we continue to unravel the mysteries of the cosmos. However, some theories suggest that the expansion of the universe might not continue indefinitely. Instead, it could eventually reverse, leading to a massive collapse, the so-called Big Crunch. This process would be followed by another Big Bang, potentially creating a new cycle of existence. If such a cycle were to unfold, it raises the possibility of a transitional phase between the end of one universe and the birth of the next. This transitional period could be characterized by conditions so extreme that they defy everything we currently understand about the cosmos. The laws of physics, as we know them, might cease to operate in any recognizable way, giving way to a state of pure energy before matter begins to reemerge. Speculative models surrounding this concept further suggest that information, or even fundamental constants of nature, might be transmitted through the boundary between one universe and the next. Yet, these ideas remain firmly in the realm of speculation. Our current understanding of the universe, shaped by observational evidence, supports the theory of a continuously expanding cosmos, not one that cycles back in on itself. The notion of cyclic universes, although captivating, faces substantial theoretical hurdles that have yet to be overcome. As our comprehension of cosmology continues to advance, we may begin to unravel these enigmatic questions about the universe's ultimate nature and its potential history. At the point where the universe may loop back upon itself, our understanding of the fundamental forces of physics would be tested in ways unimaginable today. Gravity, electromagnetism, and the strong and weak nuclear forces, forces that we consider to be the bedrock of our reality, could behave in radically unexpected ways. Time and space, which are typically treated as separate and distinct dimensions, might intertwine in a manner so complex that distinguishing between the past, present, and future could become virtually impossible. The very fabric of space-time could stretch and distort to such extremes that it might alter the way we understand cause and effect, perhaps rendering it non-linear or even allowing it to occur in reverse. The properties of particles, which are governed by the strict rules of quantum mechanics, might become impossible to predict. Instead of existing in single states, particles could exhibit properties that defy our models, potentially existing in multiple states at once, or behaving in ways that are completely contradictory to our current understanding of physics. The conservation of energy, a cornerstone of modern science, might face challenges or be entirely redefined, leading to the emergence of energy and matter in forms previously thought impossible. In this extraordinary environment, exotic forms of matter and energy might emerge. These new entities could possess characteristics so foreign to our scientific framework that they defy any easy categorization. These profound shifts in the behavior of physical laws would undoubtedly have far-reaching implications for the cosmos. The way galaxies, stars, and planets form could follow patterns vastly different from what we observe today. The potential for entirely new forms of cosmic structures, ones beyond our imagination and detection capabilities, could be on the horizon. As matter and energy approach the point where the universe loops back upon itself, they would enter a region where our understanding of physics no longer holds. This boundary marks the edge of everything we currently know about the universe, where the very laws that govern the cosmos begin to break down. Crossing this boundary would expose matter and energy to conditions of such intensity and extremity that they could undergo transformations no human has ever observed. Gravitational forces would become so immense that they could stretch and compress matter to unimaginable extremes, pulling atoms apart and perhaps even altering the properties of subatomic particles themselves. In such an environment, energy density would surge, potentially converting matter into pure energy, in accordance with Einstein's famous equation, E=mc². As this energy crosses the boundary, spacetime itself would be so severely bent and warped that light might follow circular paths or become trapped in an eternal loop. Time, as we know it, might lose all meaning, with cause and effect operating in reverse or simultaneously. This looping threshold represents a boundary beyond which our current theories cannot accurately predict what might occur. It suggests that entirely new laws of nature could be at play, offering a frontier for future scientific exploration and understanding. In a universe where the cosmos is connected or finite, we could encounter fascinating phenomena at the boundaries where the universe loops back on itself. If such a model were true, the regions where the universe folds upon itself might exhibit unique characteristics that set them apart from the rest of the universe. One possible manifestation of this could be a form of gravitational lensing, unlike anything we've observed elsewhere. Light from distant galaxies might bend and warp in strange ways as it passes through these connecting regions, resulting in unusual patterns or duplicate images of the same celestial objects. Astronomers might detect multiple versions of a single galaxy or star cluster, each appearing at different angles or distances due to the universe's peculiar geometry at these junctions. Another intriguing possibility could be the existence of cosmic strings, hypothetical defects in the fabric of spacetime. These cosmic strings, if they exist, might be more concentrated at the points where the universe loops back on itself. They could cause noticeable disruptions in the cosmic microwave background radiation or generate unique gravitational wave signatures that our detectors might pick up. The very structure of the universe could reveal hidden correlations between seemingly distant regions. Patterns in the distribution of galaxies or even anomalies in the cosmic microwave background might show unexpected symmetries or repetitions, suggesting a hidden connection between distant parts of the cosmos. Such observations could challenge our current understanding of the universe's structure and provide evidence for a finite or connected universe, a model that remains speculative but nonetheless captivating. The evolution of galaxies, stars, and planets in such a looped cosmos would follow entirely new dynamics. As space curves back upon itself, the movement of matter and energy could trace intricate paths, altering the fundamental processes that govern cosmic structure formation. In this model, galaxies might collide with themselves, as distant parts of the same galaxy encounter one another through the looping mechanism of the universe. These repeated encounters could lead to unique gravitational interactions, such as more frequent galaxy mergers, resulting in shapes and structures that defy the expectations of modern astronomy. As material is recycled through the cosmic loop, it could affect star formation rates. Periods of intense star formation, known as starbursts, might occur more frequently, while the aging of galaxies might also be accelerated in some cases. Stars within these looped galaxies could find themselves in gravitational environments unlike those in our current observable universe. The forces acting on them from multiple directions could alter their orbits and potentially destabilize the star systems themselves, influencing the stability of planets orbiting these stars. This could lead to more chaotic stellar motions, where close encounters between stars become more common, with significant consequences for the formation and survival of planetary systems. Planets within these looped regions would face unique challenges as well. The altered gravitational landscape could have profound effects on planetary migration patterns within protoplanetary disks, which might lead to more varied planetary system architectures than those we observe in our own universe. The recycling of material through the loop might also change the chemical makeup of planets, potentially giving rise to exotic planetary types that defy our current understanding of what a planet can be. The concept of cyclic universes raises tantalizing questions about the persistence of life and civilizations across vast periods of time. If the universe undergoes periodic cycles of birth and death, it's possible that the conditions between these cycles could be so extreme that no life form could survive intact. The immense energies involved, along with the gravitational forces at play, would likely obliterate all existing structures, galaxies, stars, and even subatomic particles, each cycle potentially marking the complete destruction of everything that existed before it. However, as our understanding of physics continues to evolve, so too might our perspective on whether life, or even civilization, could endure across these unimaginable transitions. However, some speculative ideas suggest that information or patterns might carry over from one cycle to the next. This notion proposes that the fundamental laws of physics, or even more intricate structures, could be encoded within the very fabric of space-time itself. If such a mechanism existed, it might offer a framework where life or civilizations could be reborn in subsequent cycles, although potentially in forms we would not recognize. From another perspective, the multiverse theory offers a fascinating alternative. According to this theory, our universe is just one of many, each existing as its own distinct bubble in a larger multiversal structure. In this scenario, civilizations may discover methods to traverse or communicate between these various universe bubbles, effectively enduring across multiple cosmic realms. While these ideas remain purely theoretical, they challenge the limits of our imagination and push the boundaries of scientific exploration into the true nature of our cosmos and the potential for life within it. The concept of a periodically resetting universe would radically shift our current understanding of cosmic evolution. Instead of perceiving the universe's history as a linear progression stretching from the Big Bang to the present day, we would need to embrace a cyclical model. In this framework, the universe goes through phases of expansion, contraction, and eventual rebirth. Each cycle might begin with a new version of the Big Bang, setting the stage for the formation of galaxies, stars, and planets. As the cycle advances, these cosmic structures would evolve and change, following a pattern similar to our current understanding. However, the key difference lies in the fate of the universe at the end of each cycle. Rather than heading toward the inevitable heat death or big freeze, a cyclical universe could experience a dramatic reset. This reset could take the form of a big crunch, in which all matter collapses back into a singularity, or it might involve some more exotic mechanism, one that reboots the cosmos altogether. Following this reset, a new cycle would commence, potentially with different initial conditions or even altered physical laws. Such a cyclical model presents profound questions about the nature of time, causality, and the survival of information or patterns across cycles. It compels us to reconsider our ideas about cosmic history and the uniqueness of our current universe, suggesting that what we observe may merely be one iteration in an endless sequence of universal cycles. As we entertain the possibility of a cyclical universe, we must explore whether remnants from previous cycles might persist through the Big Bang. Some theoretical physicists have proposed that certain large-scale structures in our universe could carry imprints or echoes from earlier cosmic iterations. These hypothetical remnants, often referred to as cosmic fossils, might be detectable within the cosmic microwave background radiation or in the way galaxies are distributed across the observable universe. For example, some researchers hypothesize that anomalies in the cosmic microwave background, such as unexpected cold spots or unusual alignments, could indicate the presence of collisions between our universe and others within a multiversal scenario. Another intriguing possibility involves the largest structures in our cosmos, such as galaxy superclusters or cosmic voids. These massive structures might retain some memory of previous universal cycles, suggesting a legacy from earlier cosmic eras. However, it's important to recognize that these ideas remain highly speculative, as the concept of a cyclical universe presents significant challenges. Chief among these challenges is the question of how information or structure could survive the extreme conditions of a big crunch or big bounce. As observational techniques and theoretical models continue to advance, we may uncover more clues about the true history of our cosmos. These clues could eventually reveal hidden evidence of past universal cycles embedded within the fabric of space and time. The idea of a looped universe opens up exciting possibilities regarding the long-term fate of matter and energy. In this model, rather than expanding infinitely or collapsing back into a singularity, the universe would form a closed loop in both space and time. Such a configuration could have profound implications for the ultimate destiny of everything within it. One of the most significant consequences of a looped universe is the potential for matter and energy to never truly be lost or destroyed. Instead, they would cycle through different states and configurations as the universe completes each loop. The arrangement of galaxies, stars, and other cosmic structures would reset at the end of each cycle, creating a perpetual cycle of creation and destruction on a grand cosmic scale. This cyclical nature would also have profound implications for entropy, the universal tendency toward disorder. In a looped universe, the increasing entropy we observe today could be periodically counterbalanced by moments of decreasing entropy as the universe nears the end of each loop. These moments of decreased entropy could lead to a cosmic renewal where the universe reverts to a more ordered state. Furthermore, a looped universe might allow for the preservation of information across cycles. While individual objects and structures would be destroyed and recreated with each cycle, the fundamental patterns and laws that govern the universe could persist. This continuity might allow the universe to maintain a form of cosmic memory, which could, in turn, influence the evolution of matter and energy in subsequent cycles. This idea opens up a fascinating prospect that our universe, as we know it, might be only one iteration in an ongoing cosmic story, its current form shaped by the patterns of countless cycles that preceded it.